Hello, everyone. Um, so I am very pleased to begin OpenCogCon. It's the conference for OpenCog and OpenCog developers and users. And Benjamin Gertzel is going to be our keynote speaker today. And so I think it's worth beginning by thinking back to when OpenCog was first announced way back in 2008 at the very first Artificial General Intelligence Conference at the University of Memphis. So Ben and David Hart had worked together and put together this concept of open sourcing what was then the Novamente cognition engine or portions thereof. And that was the beginning of OpenCog. And this year we're beginning to rethink based on a lot of use cases and changes in both technology and ideas, how the overall framework. Basically, we're preparing for the next generation of OpenCog 2.0, so to speak. So today, Ben's going to essentially set the stage for what this next generation might look like. Dr. Ben Gertzel, take it away.
Yeah, thanks a lot, Matt, for that intro. And Matt is one among a number of colleagues who've been working with me on this since the beginning. I mean, and since before the beginning of OpenCog. Matt and I have been collaborating on AI and associated projects since 1993, I believe, well before the term AGI or the OpenCog software existed. And as Matt said, OpenCog has been around since 2008 and building on code that was being developed but hadn't yet been open source before. The oldest pieces of code go back to, I think, fall 2001 or something. And, there's a history there, which I'll talk about a little more toward the end of my talk. But I'm always a person who's more interested in the future than the past. And the thinking and prototyping and experimenting that we've done working toward AGI using the OpenCog system during the last decades, it's valuable for the knowledge it's put into the minds of all of us who have worked with it, and it's most valuable for what it gives us in terms of a platform of knowledge, software, experience for moving forward toward AGI. Because I mean, while the AI world is a totally different place than it was in 2008 when we launched OpenCog, or in 1993 when Matt and I started working together on AI. Nevertheless, in spite of all these changes, no one has created AGI yet. We don't have AI that's capable of generalization, imagination, self-understanding, creativity, and compassion, and all these other traits that characterize human-level general intelligence. So in spite of all the amazing advances in AI, and in spite of the fantastic pace at which the AI field is now developing, which makes things a hell of a lot of fun now compared to in prior phases of the AI field, regardless of all these things, there's still a huge leap to be made to get from where we are now toward human level AGI. And I believe once that leap is made, once we get from where the AI field is now, where we really don't have human level AGI working in OpenCog or anyone else's project, once you make the leap from where we are now toward having human level AGI, I think then we're going to see an even faster acceleration as that AGI improves its own intelligence in ways that humans can't even imagine. But for now, I think we're poised at the point where we have the computer hardware, we have the algorithms and the cognitive understanding, we have the software libraries and principles, and we're at the point where we're really poised to make the leap finally to general intelligence, which Matt and I and many others have been working on for so long. And I think that OpenCog is the right framework for catalyzing that leap, for making the jump finally to true AGI. And I'm giving one talk at this OpenCogCon 2-day online event. I'm giving one talk this morning Pacific time where I'm sitting, and then another one 24 hours from now. And what I'm going to do today is review some of the basics of OpenCog. Sort of what are the objectives? What's the system trying to do? What are some of the high level ideas underlying it? What are some of the core algorithms? What broadly is the OpenCog community thinking of for the future going forward? So this will be a fairly high level talk, much of which will be familiar to those who have been around the OpenCog world for a while. But of course, there's going to be some in the audience who haven't been, and for whom this will be more new information. And then in my talk tomorrow, 24 hours from now, I'm going to go in depth into what a group of us have been thinking regarding a radical redesign and substantial re-implementation of OpenCog, which we had been referring to as OpenCog 2, sort of tongue-in-cheek, because the existing version of OpenCog really isn't at 1.0. It's probably more at 0.1. But I mean, we're nearing the singularity, so why not leap from 0.1 to 2? But after some thought, we decided to get rid of numbers and start using the names of elementary particles for OpenCog versions. So we're working on not OpenCog 2, but OpenCog Hyperon, where Hyperon is one of the very, very funky elementary particles that the physicists have discussed. I mean, appropriate in that the lead developer of OpenCog 1, Linus Vepstas, is a particle physicist with a PhD in string theory. So maybe after OpenCog Hyperon, we can go on to OpenCog Tachyon, which can go back in time and fix all the mess we've seen in the past. So anyway, tomorrow morning I'm going to go in depth into thoughts on the OpenCog Hyperon architecture and how I think we may want to re-architect, re-implement, restructure things in OpenCog for the future. Today I'm going to give more of a general overview regarding what the hell OpenCog is and why anyone should care about it in an era where there's so many different AI frameworks out there. In terms of the structure of the event, so today we have this keynote by myself, then we have a session on applications of OpenCog to bio-AI and bioinformatics. And then we have a keynote by Linus Vepstas, who's been the lead developer of OpenCog during the present and past period. Then tomorrow, the session is focused on OpenCog Hyperon and sort of brainstorming and presenting what work we've done so far regarding how to refactor OpenCog and rebuild OpenCog so that it is even better than it is now and is suitable for creating true artificial general intelligence. So the bio-AI application that will take up much of today's session, I mean, on the one hand, it's a very particular application, though an important one, because it pertains to all of our health and life. But I think it's also interesting in a more general way, just as a specific example of stuff being done with OpenCog, because tomorrow we're plunging into how do we rebuild OpenCog to be better and better so that it's capable of general intelligence. But in thinking about that, obviously we're not just building something totally new out of nothing. We're incorporating everything we've learned from OpenCog and predecessor systems that the OpenCog team has worked on. And to talk about those lessons concretely, it pays to have a particular use case in mind, and the applications of AI to reasoning about biological systems it's a use case that a number of us are actively working on right now. So let me pause for a moment and get Zoom to share my screen, and I'll go through some slides giving an overview on OpenCog. All right, so is screen sharing working all right?
Yes.
All right, let's assume so. And so I'm going to give a run through some of the background of why OpenCog was created, and in general, what sorts of things we want it to do. I'll go over then the basics of OpenCog architecture and concepts and algorithms, and then just drop a few hints about the OpenCog Hyperon next generation stuff, which we'll really plunge into more tomorrow. This is a lot of material to go through quickly, but there's other talks I've given, as well as a lot of papers that cover some of this ground, although not all aggregated together in the same way. So we're after AGI here with OpenCog, and I mean, the formal definition of AGI is itself a research topic. I mean, in Marcus Hooter's book Universal AI, he gives a definition of AGI in terms of the ability to, achieve any computable reward function in any computable environment. But this it's an interesting direction, but it doesn't take into account resource restrictions nor the particular nature of our physical universe. So I mean, there's no really agreed on formal definition of what is AGI, but conceptually what we mean is the ability to generalize and transfer knowledge and imagine and create, so that the AI can deal with situations that are qualitatively different than situations it has encountered before. And it's pretty clear that human beings can do this in a sense that no current AI program can. I mean, current AI programs can do some amazing things that no human can do, but they're a little more restricted to what they were programmed or trained for, rather than being able to deal with radically different situations. And I think this is not an intrinsic limitation of computer software. It's just a limitation of the AI software that we have right now. And if we, if one digs into cognitive science and cognitive psychology, you can see all the different aspects of human general intelligence, perception, actuation, and movement, many different types of memory that we have, types of learning that we can do, which is reinforcement, imitation, interactive, experimental, many kinds of reasoning, including causal and hypothetical, as well as deductive and inductive. Can do strategic and tactical planning. We're very good at allocating attention on multiple different time scales. We have a motivational aspect where we can learn new goals and sub goals and throw out our goals when in some broader sense they're not working for us. We have emotional intelligence, the ability to model ourselves and others. We have social intelligence. We can communicate using language, pictures, gestures, more abstract formal systems. We have quantitative and geometric intelligence. We have intelligence for building things, be it Lego constructs or corporations. So all these are aspects of how the general principles of general intelligence, as they're articulated in the work of Marcus Hooter and others, manifest themselves in the specific context of human beings whose general intelligence is oriented toward controlling particular kinds of bodies in a particular kind of physical world. So if you're curious more, so for my own thinking about what is general intelligence, I had a blog post on my blog, The Multiverse According to Ben, which was titled General Theory of General Intelligence, GTGI. And in that blog post, I linked to a long list of research papers that I'd published over the years, giving bits and pieces and thoughts of a general conceptual theory of what is general intelligence. And there's a part of my mind that would like to set aside practical work and building stuff and just focus for like 5 or 10 years on figuring out the mathematics and philosophy of what is general intelligence, so that we have a theory of general intelligence that does for AI what, say, the Navier-Stokes equations of fluid dynamics and the theory of aerodynamics does for flight. On the other hand, while it would be satisfying to work out a theory like that, I sort of feel like we're at a special moment in history when it's actually possible to build an AGI system based on the engineering tools we have at hand and based on the partial and fragmentary bits of AGI theory that we have at hand, and then evolve the theory alongside the building of the system. And we're focusing more on the building of the system and the practical side in these 2 days of OpenCogCon, because OpenCog is a particular system. On the other hand, I think it is important to work toward a theoretical understanding as much as you can, and to use the bits and pieces of general theory of general intelligence that we do have to inform our design decisions that we use in building the AGI. And this has to do both with the mathematical structure of what is general intelligence in the most high level sense, and with the particular kinds of general intelligence that are manifested in the human context, which has to do with the sort of laundry list of capabilities I've just gone through. I mean, in principle, one might approach AGI by taking the most general type of general intelligence, like an AI-XI system, like Marcus Hutter has identified for optimizing any computable reward function in any computable environment, or something even more general than that, a sort of open-ended intelligence with this sort of maximal power. One might be able to design an AGI by taking this sort of maximal theoretical general intelligence and like program specializing it to the particular problem of general intelligence in a human-like environment. In practice, we don't have the theoretical or practical tools to quite approach it that way, but that's partly underlying the thinking that my OpenCog colleagues and I have brought. Like, how do we take the general nature of general intelligence and see how it manifests itself in the particular case of human level AGI and human-like AGI. Now, I've been thinking hard about AGI, I mean, honestly, since I was a kid in the 1970s, and certainly since I got my PhD in 1989 and doing prototyping and experimentation. When I launched together with a number of colleagues the Artificial General Intelligence Conference Series in 2006 with the first AGI workshop, then 2008, the first AGI conference, as Matt alluded to. Then, we had the feeling of a bunch of mavericks huddled in the corner while the mainstream of the AI field thought general intelligence was something not to be taken seriously whatsoever. I mean, now things have changed, and, national leaders know what AGI is. Vladimir Putin mentioned AGI in his talk at the AGI Journeys conference last fall. I'm not sure Trump knows what it is yet, but that's a different conversation. And of course, large corporations are now considering AI as part of their critical strategy, and many large companies are thinking about AGI as well as narrow AI. Microsoft, as almost all of us know now, has invested $1 billion into OpenAI, and I'm showing here in the slide Ilya Sutskever, one of the founders and director of OpenAI. I mean, he has come out now saying near-term AGI is a serious opportunity, and we just didn't have folks associated with major corporations publicly saying this 5 years ago, let alone 10 or 15 or 20 years ago. I guess Google DeepMind has been at it between 5 and 10 years. That was sort of the beginning of the invasion into the corporate arena of AGI, which was an interesting one for me, both because what they're doing is really cool, and because one of their founders, Shane Legg, worked for me in my AI company WebMind in the late 1990s. So I think we're we're at an inflection point in the opportunity for AGI. AGI is finally being taken seriously now, but there is still no AGI, right? And if you look at this in the broader context of the history and development of AI, you can see we've experienced a narrow AI revolution that's well underway. Narrow AI is transforming everyone's lives, and it's going to be doing so more and more and more by automating an awful lot of jobs now done by humans, and achieving all sorts of practical things that humans just can't do now. We're not yet to AGI. Once we get to AGI, that AGI may well be to rewrite its own code and self-modify to work toward artificial superintelligence. But first, we got to get to AGI. And I have proposed in a blog post last year that one way to think about the transition from narrow AI to AGI is through what I call neuro-AGI, which sounds like a stupid oxymoron, and maybe it's not the most brilliant term I've ever come up with. But what I mean there is general intelligence that does have the key characteristics of human level general intelligence, but is primarily focused on a particular domain. Of course, humans are narrow AGIs compared to a mathematical, theoretically possible, truly general AGI also. Like I'm much better at running a maze in 2 or 3 than 750 dimensions. There's certain things that my human level intelligence is better at than others. So if one had say an AGI that displayed human-like general intelligence in biomedical research, or an AGI that displayed human-like general intelligence in the context of coordinating a smart city, even if each of these systems didn't display human-level AGI across all vertical areas, it could still have general intelligence in the sense that current narrow AIs do not. And in terms of the practical development plan of OpenCog, I think one interesting direction is to work from narrow AI toward AGI through sort of vertical application specific general intelligences, and the bioinformatics proto-AGI work that is going to be talked about by a number of speakers later this morning. One aspect there is working toward a narrow AGI biomedical researcher. And while it hasn't been framed in those terms, I think the commercial promise of narrow AGI is one of the reasons why we are seeing these large corporate investments in the AGI R&D organizations in recent years. So, what is AGI is a long story, and I've given talks on that before. And actually in the workshop on day 1 of the Artificial General Intelligence 2020 online conference, which was just a few weeks ago, in the first workshop of that conference, I had a talk going through some ideas on general theory of general intelligence. Now I'm just going to articulate a few simple ideas, enough to structure the following stuff I want to say about narrow AGI and OpenCog. So we can look at one of the core principles of general intelligence as using in perception and memory to do prediction of what actions will achieve goals. Now you could build a narrow AI that did this in a sense also, but in fact most narrow AIs are not really combining all these aspects in a non-trivial way, although you could say they're doing it in a very simplistic way. And then in addition to this goal-oriented and prediction-oriented aspect, there's an aspect of AGI which you can refer to as open-ended intelligence, where it's not all goal-oriented. Complex AI systems are complex self-organizing systems that are just transforming themselves and transforming their environment in a coupled way, and evolving new forms and patterns, more in the matter of an artificial life system. And Weaver, David Weinbaum, who's been a close friend and a sort of advisor of myself and OpenCog and SingularityNET for a while, he had a beautiful PhD thesis entitled Open-Ended Intelligence, which explores this aspect of what intelligence is. Now, the opposite of broad open-ended intelligence, which can achieve a wide variety of goals in a wide variety of environments, which we're thinking of as the aspiration of our AGI work with OpenCog. The opposite of this is an AI system that carries out one very narrow task based on either very narrowly defined programming or a narrowly configured set of training data. And this highlights the need to distinguish what we're pursuing with OpenCog with most of what's being done with current deep learning systems, which are are amazing. I'm really happy to have machine translation that works as well as current machine translation does, and OCR that works as well as it does. And there's face recognition. There's been many amazing achievements of current deep neural net systems, and it, in a way, it blows my mind given how limited multi-layer neural nets were when I used to teach neural nets in the 1990s, back when I was an academic. On the other hand, it's important to clearly understand the distinction between these deep neural nets and other narrow AI machine learning systems that are achieving so many cool practical things in the world today, and AGI such as we're trying to build with OpenCog. And Gary Marcus, who is a friend of mine who has his own AI company now, and he had a previous one which was acquired by Uber. He has written a couple essays highlighting in great detail the limitations of current deep neural nets. There was a essay a few years ago, and then a more recent one just highlighting the limitations of GPT-2 language models. So anyone who wants to explore conceptually what current deep neural net models can and can't do, you look up Gary Marcus's papers on the limits of deep learning. But I mean, the core is they lack strong generalization. I mean, they're very good at identifying the patterns in their training data sets, and not good at making a leap to something qualitatively different than the training data set. And for some applications, this doesn't matter. Like if you're trying to solve face recognition, there's not that many people with three noses on their forehead, or people walking around looking like Picasso paintings. Once we have enough training data of human faces, that being able to recognize the patterns in that training data is good enough for face recognition. If you are, on the other hand, dealing with, say, political decision making or biomedical discovery, then you're dealing with the radically unknown at each step. And you really need a system that can be much more agile and deal with situations that are fundamentally different than anything they'd seen before. Current deep neural nets are not doing that. And how to get to an AGI relative to current deep neural nets is an open question, right? So some AGI researchers believe that current deep neural nets and the whole field of machine learning are just orthogonal to and off to the side of AGI. And Douglas Hofstadter, whose book Gödel, Escher, Bach was the first sort of introduction I had to the scientific research field of AI when I read it in the mid-1970s. I mean, that Gödel, Escher, Bach presented a totally different way of looking at intelligence, which is not based on recognizing patterns in scalable data sets, but just on fluid imaginative leaps. So the Hofstadter point of view will be that current deep learning is just a totally different thing than general intelligence. On the other hand, many researchers in the deep learning field, including some very brilliant minds who I respect greatly, like Yoshua Bengio, for example, have more the idea that you can incrementally improve current deep learning systems bit by bit, so that one of their descendants can have real AGI. Another point of view, which is closer to what we're doing with OpenCog, is hybrid architecture, thinking, well, deep neural nets are cool, they're great at perception processing, they may be good at some kinds of reinforcement learning. They're also missing a lot of things. So why don't we make a hybrid system where we incorporate neural nets, also incorporate other sorts of AI algorithms like logic systems, artificial life systems, evolutionary program learning systems, and by integrating together AI from different paradigms, perhaps we can create something that achieves AGI via synergetic interactions of these components. And this is the point of view that underlies OpenCog, and you can actually look at some of the recent achievements in the deep learning field as being hybrid architectures in their own way. I mean, AlphaGo has a couple neural nets, and then a sort of a game tree, which is not a neural net, and a few of the architectures out there in language processing, like Ernie from Tsinghua University. I mean, this has a knowledge graph integrated with a deep neural network. The DNC, differential neural computer architecture from Google DeepMind, you could view as a hybrid in its own way. But these hybrids are neural net centered hybrids, whereas OpenCog, as I'm going to talk about, is not so neural net centered. They're really OpenCog neural nets can be there, but other things have a primary or greater role. And neuro-symbolic integration from this point of view is one aspect of hybrid AGI architectures. And you can look at it like neural nets are really good at certain kinds of pattern recognition. Symbolic AI, logical reasoning systems, are very good at certain kinds of abstract inference. And then maybe if we put them together in the right way, you get something that can do abstract inference in a way that's fueled by the patterns recognized in large data streams, right? And, you know, there's a bunch of work we've done on that using OpenCog and neural nets in both the vision and language domain. Alexei Potapov, who will be giving a talk tomorrow in this event on the OpenCog Hyperon next generation stuff. He's had a few papers and some blog posts on the SingularityNET blog going over some steps toward neuro-symbolic AI that have been taken, putting deep neural nets together with OpenCog. We're also doing some neuro-symbolic stuff in the bio AI domain from a different direction that will be talked about today. From the hybrid AGI architecture view, connecting neural and symbolic is just one aspect of connecting together multiple different algorithms into an integrated AGI system. And there, you know, neural symbolic stuff has had some interesting practical applications already. On YouTube, you could find a talk by Hugo Latopi from Cisco's Office of the CTO, describing some work that was done with Cisco and SingularityNet using OpenCog and deep neural nets to do some reasoning about street scenes, where deep neural nets were processing the output from cameras, looking at street scenes from different positions. Then OpenCog combined together the patterns that were read out from multiple cameras to come up with general conclusions and inferential predictions based on what was happening in the street scenes. But I mean, street scene analysis is just one possibility. We're doing some research now on neuro-symbolic language processing. Andres Suarez had a paper on that at the recent AGI conference on language learning using neural nets to recognize patterns in large corpora, and then using symbolic reasoning to infer a grammar. And there's a number of other important aspects here. I mean, probabilistic programming is quite interesting and can be part of the neuro-symbolic bridge, because I mean, probabilistic programming has been used as a sort of wrapper for model learning of neural networks. You had things like the Edward framework that did that in a quite limited way. Then you have probabilistic logic, such as OpenCog's PLN framework, which is on the symbolic inference side. So connecting the probabilistic logic in systems like PLN with probabilistic programming as used as a paradigm to wrap up neural net model learning, you have sort of abstract probabilistic structure manipulation as part of the glue between the neural and symbolic sides. And evolutionary computing pops up there. I mean, Alexei Potapov again had a paper a few years ago in one of the AGI conferences looking at evolutionary learning and probabilistic programming together, where you're looking at evolutionary learning as a sort of substitute for the crude Monte Carlo sampling done behind the scenes in many probabilistic programming algorithms. Evolutionary learning has some power to create new things and create amazing new forms. You see that in that we were all created by, in large part, evolutionary processes together with, you know, self-organizing biochemical processes. And having processes of simulated evolution in your AI system, I think, can give a sort of creativity and imagination that neither logic nor current neural nets easily comes by. And there's all these different aspects of different AI algorithms you could pull together into an AGI system. And of course, there's many different hybrid AGI systems one could build. OpenCog is a particular approach. And if you want to understand the concepts behind OpenCog in more depth, the books Engineering General Intelligence, parts 1 and 2, which were written mainly by myself, Neil Geisweiler, and Cassio Penishine, I think published in 2014, but the book was a long product before that. That lays out the algorithms and concepts behind OpenCog in a fair degree of detail. Some middle chapters of my book, The AGI Revolution, review the same ideas from a somewhat less technical perspective. But in the next few minutes, I'm going to give a high-level overview of what's there, and I'll go over some of that more tomorrow morning in the context of the plans for the OpenCog Hyperon architecture. So, there's a lot of ways one could build AGI, right? You could make a single core cognitive process. You could have multiple simple processes cooperating together, like in an artificial life framework. You could have a number of complex cognitive processes interacting together. Of course, this is the hybrid approach, which OpenCog is pursuing, and which the human brain may be viewed as pursuing in a different way, and that we have all these different neural subnetworks, hundreds of them with different architectures that are interacting in a different way. And you have a number of aspects here, right? You have learning algorithms, which has been the focus of a lot of the AI field in recent years. Then you have the cognitive architecture, like how are the different kinds of processing and memory being done by the system arranged. And there was a whole discipline of cognitive architectures in the AI field, which is still going with architectures like SOAR and ACT-R. And the idea there is the cognitive architecture, the ways different kinds of processing memory are arranged is the most important thing. And you could sort of drop any learning algorithm in there. Whereas current machine learning and deep neural nets is focused more on learning and less on cognitive architecture. It may be that both are critical, and yet you have to get them to work together very well. And it may be that, again, there's the question of, to what extent are the knowledge representations, the way the system represents knowledge internally, to be engineered by the human system architect, versus to what extent are the system's internal knowledge representations something that has to emerge through the system's learning and growth and engagement with the world. And again, and maybe both of these aspects exist. So with OpenCog, we're aiming to make a hybrid AGI system, which includes multiple fairly complex algorithms that are dealing with different kinds of learning and different types of memory that interact together in a synergetic way, and where some of the learning and representation is, explicitly, initially it's engineered by the human developers, and then some knowledge representations and learning strategies are things that emerge in the system in the course of its ongoing growth. And one of the theoretical concepts that's key here is cognitive synergy. And if you look in Archive in the papers by Ben Gertzel, you can see a paper giving a sort of category theoretic formalization of the concept of cognitive synergy. But the basic idea is, if you have multiple AI algorithms working together, for them to really form parts of a productive hybrid AGI architecture, what you need is, when one of the AI algorithms gets stuck and confused about what to do next, then the other AI algorithms in the mix have to be able to jump in and help it out where it got stuck. And the trick is, in order to achieve this sort of cognitive synergy, you need the multiple AGI algorithms in that cooperative network to be able to inspect each other's internal and intermediate representations. Like, if I get stuck solving a problem and I'm halfway there and I want you to help me get unstuck, I need to be able to explain to you the intermediate state, in my mind as I'm halfway to solving the problem, right? And this means, in a sense, the multiple algorithms involved in a hybrid AGI system, the multiple algorithms need to have a common representational substrate. And in OpenCog, this is the atom space, which is a weighted labeled hypergraph. And actually, the final keynote of today's OpenCogCon event will be Linus Vepstas, the principal architect of the current OpenCog atom space, just going in some depth on how the atom space work. But we have this weighted labeled hypergraph knowledge store, which has nodes and links that can point to links, links that can point to multiple nodes, even links that can point to whole graphs. And there's different types on the nodes and links, and there's quantitative weights on the nodes and links. And this serves as the common representation for multiple different AI algorithms, including neural nets, probabilistic reasoning, evolutionary learning, motivation, and so forth. There's some resemblance to what was called in the 1980s a blackboard architecture. Like, you have a blackboard. We didn't have whiteboards back then, right? You had a blackboard, and the multiple AI algorithms are like a bunch of guys on the blackboard, writing stuff for each other to see, erasing stuff, sort of building the same picture together. So the concept of having a common knowledge store that multiple AIs cooperate on sharing their intermediate representations as well as their conclusions. That high-level concept is not new, but getting it to work has been a long labor, right? And you can look at this in terms of the multiple kinds of memory that human-like minds need to routinely and efficiently deal with. I mean, we have sensory memory, episodic memory of our life history, procedural knowledge of how to do things, declarative knowledge, which is sort of semantic knowledge of facts and beliefs, attentional knowledge of what to pay attention to in what context. And we can represent all these kinds of knowledge in a way that's centered on the OpenCog atom space, sometimes with some auxiliary data structures pointed to from within the atom space. And we then have different learning algorithms that are specifically focused on these different kinds of knowledge. For example, our probabilistic logic networks reasoning system focuses on declarative knowledge, and we've largely used evolutionary learning to focus on learning procedural knowledge. We've largely used neural nets so far for allocating attention or for dealing with data processing in sensory data, so sensory knowledge. The nodes and links in the atom space are, in many cases, an explicit knowledge representation. Like, I mean, you could have a cat node and an animal node with an inheritance link between them, but it can also be implicit knowledge representation, like the OpenCog system's representation of a cat or of Dr. Matt at Clay or whatever it is. It could be a large activity and linkage pattern of many different nodes and links across the atom space. So not all the representations have to be baked in at the micro level. Some of them can be emergent at the higher level. So Linus will go over this more in his talk at the end of the day, but I mean, OpenCog atom space has two kinds of atoms, nodes and links, and this store of nodes and links has weights on it. So there's values of many kinds. Two of the most critical values are truth values. Many nodes and links have truth values representing probability or fuzzy truth. Many of the nodes and links have attention values, telling you how important those nodes and links are in the short or long term. And here's just a few examples of nodes and links in the system. So you could have a member link saying like a certain person or animal is a member of a certain family. Well, this is a slide I made in 2008. I miss that rabbit who's shown there. She's been dead for a while. That was a great rabbit. You can have Hebbian links, which indicate common association. Like two nodes have a Hebbian link if they were often important at the same time, and that's something from the neural net field. You can have context links representing that a certain set of links are applicable in a certain context, and many of the algorithms acting on this hypergraph have their own whole science behind them, right? So there's a book on probabilistic logic networks that gives the math behind the probabilistic logic on the truth value weights and the nodes and links. And there was another later book on real world reasoning that goes into more detail on things like spatial, temporal, contextual, and causal reasoning. Moshe Lutz's 2006 PhD thesis went over many of the principles behind the probabilistic evolutionary program learning that we use to learn little programs that are then embedded in the atom space to do practical things. That's a part called Moses, and we'll encounter both of these later today in simple forms in our work on bio-AI. Concept blending is a powerful heuristic for creativity. If you have a gerbil node and a human node, and you fuse them together, you may get a gerbil man node, right? Which is not that creative on its own, but then gerbil man may get all sorts of other cool characteristics. Now here's another example of concept blending. You want to put a robot together with a person, and you get a robo person. And this is another ancient and nostalgic slide. That's actually my wife Ray Ting a couple years before we got married. So, and we have not yet put her head on top of a now robot. However, that's maybe say for OpenCog tachyon. Concept formation can occur in a whole bunch of different ways. Blending is one. Another one is if you have a bunch of nodes that are commonly active, like say cat, mouse, tail, and furry are often active at the same time. You may just group them into a common concept that's then symbolized by a node, which can then be manipulated by explicit reasoning and other algorithms. And Then the truth values are dealt with by logical reasoning and other such methods. Attention values are dealt with by more neural net type methods, where attention can spread through all the nodes in the network. And this is more like activation spreading, as happens in old style formal neural networks, and it models the flow of attention through the human brain. And Matt Clay, who introduced me, has actually done a lot of work on this, on the mathematics of attention flow, which will get more and more important with OpenCog Hyperon as we move toward more and more scalable systems. Integration of deep neural nets with the semantic network of OpenCog is highly important. Also, you can do that a few different ways. I mean, you can put the whole hierarchical structure of a visual cortex in the atom space, or you can leave much of that high-level structure outside the atom space and some other data structure, and then you have linkages between this neural net and nodes inside the atom space. And if you look up Alexei Potapov's paper from a prior AGI conference on cognitive module networks, then he explained some of the things we've done in the current version of OpenCog, sort of coordinating between neural net structures in PyTorch and the nodes and links inside the atom space. We've dealt with this mostly for perception, but you can do the same thing with actuation, with deep neural nets for actuation, and with goals. So you can look at deep hierarchies for perception, deep hierarchies for action, deep hierarchies for goals and sub-goals. These can be coordinated together both within the atom space and outside within libraries for efficient manipulation of scalable floating point structures and associated, say, nonlinear regression or deep neural algorithms. Now, we've used OpenCog, I'd have to say, so far with all these representations and algorithms, we've used it largely as an R&D playground for exploring with what the algorithms do, how they can all interact with each other. And we've learned a hell of a lot about what to do and what not to do, about how all the algorithms work and don't work. So it's been really an incredible learning experience about AGI. We've also used OpenCog for some practical things here and there, mostly on the back end and inside various other products or projects. So we've used OpenCog to control Sophia Robot. If you look at lovingai.org, that gives some information about experiments we did using Sophia as a meditation assistant, which was using OpenCog as a control system. And we had a paper in one of the NIPS conferences where we described that. We also, just to amuse ourselves, we measured the Tononi-Phi consciousness coefficient of the OpenCog atom space while it was controlling Sophia on meditation trials. Not that I take that fully seriously as a measure of consciousness, but it was interesting as a measure of just the emergent activity in the OpenCog atom space as OpenCog was controlling Sophia. Biomedical AI we've been working on, and we'll talk about that a bunch later today, so I won't go into it much now, but we've been focusing on longevity research, recently doing a bit of analytics related to cancer and COVID-19 as well. And one thing I've been wanting to get more into and put more time into, which comes up heavily in the bio AI domain, is computational creativity. And if you look at a blog post called Cogistry I posted a number of years ago, this explains how to go beyond evolutionary learning, something more like algorithmic chemistry, where different little codelets, little programs are rewriting other codelets to produce new codelets. You have a self-reinforcing, self-intercreating system of little program fragments all rewriting each other. And I think you can build this in OpenCog atom space. This is how you can get radical creativity way beyond human creativity. We do need a more scalable OpenCog infrastructure to support research on this sort of next generation hybrid AGI algorithm, which is part of the OpenCog Hyperon motivation. But if we go back to the high level, and I'm about to wrap up here, I mean, if we looked at deep neural nets as sort of the first explosion of AI into really vast and obvious practical applicability, I mean, not that they're necessarily the most interesting or profound AI algorithm in a theoretical sense, but they've been the first AI algorithm to make a huge commercial breakthrough. we could look, well, maybe the next step is going to be hybrid systems, putting neuro-symbolic, evolutionary, other things in the mixture. That's going to bring us to neuro-AGI via cognitive synergy among multiple algorithms doing interesting things in specific domains like robotics and bio-AI. And that's what's going to bring us on to AGI and super intelligence. And I think OpenCog has the right conceptual idea, the right set of algorithms, and all the prototyping work we've done over the years and decades gives you a whole lot of information about what to do next. I do think the time has come that we need to re-architect and largely re-implement a lot of the stuff in the guts of OpenCog, which is going to be the topic of tomorrow's portion of this event. We're going to talk about Atom Space 2.0, which is a rebuilding of the OpenCog Atom Space we're in the early stages of, with the goal of massive distributed scalability, an easier to use way to program and script structures and processes, which we're thinking of as an Atomese 2 programming language, and then better support for both meta reasoning, reasoning about reasoning, and integration of OpenCog with external frameworks like neural net framework. So I think what we've done so far is in the right direction. We need to take a little bit of a step back and improve some of the tooling, and that's what's leading us on to tomorrow's topic of OpenCog Hyperon architecture. And in my talk tomorrow morning, I'll go over all the different pieces in this OpenCog Hyperon architecture diagram and sort of explain what I think they're doing and why. And then Alexei Potapov will go into greater depth on some of the inner mechanics that we're thinking of for Atomese 2.0. So I mean, looking back at OpenCog, I mean, obviously, it's been an amazing research playground, and we've learned so much from it and built some cool back-end systems for various practical products with it. Obviously, when we launched it in 2008, we were thinking we would go faster toward AGI than what has actually happened. Like we're not remotely now in 2020 where we hope to be with OpenCog in 2008. And you know, I have obviously thought a lot about why we didn't progress faster, and I think, you know, there's a whole bunch of different factors. Certainly, the timing is just much better right now in terms of the hardware being there, software libraries being there, and broad interest in AGI. So I think right now, if we make a big push on OpenCog, as we're doing right now with this event and with OpenCog Hyperon, I think right now it's a far better time to aggregate together a critical mass of open source developers toward an AGI project. I think also the existing version of OpenCog hasn't had the scalability or the ease of use that really should have been there for the thing to take off the way that we wanted to. And while we've used it on the back end to do a bunch of cool things, we haven't had the, you know, amazing, easy to see demonstrations of what OpenCog could do that, you know, in hindsight would have been nice to have. It's just we've been focused on the core R&D and advancing our understanding, and then on building back-end practical applications, which has helped a number of us to earn our livings over the years. And we just didn't find time and focus to make the funkiest practical demos, which might have been wiser to do in terms of attracting attention for the project. So we can't fix the errors we made in the past. We can take everything we've learned in the past, and going forward to the next generation, we can focus as well as on our cool algorithms and theoretical insights in the nature of AGI. We can focus on scalability, usability, and demonstrability with OpenCog Hyperon initiative in order to exploit the timing, which is just now really, really good for AGI in a way that seems remarkable to those who have been at it so long. So we'll talk about the Hyperon architecture and algorithms more tomorrow. I want to mention now the two sort of practical use cases that we're thinking of besides the bio-AI use case that is going to occupy a bunch of this morning. So in addition to bio-AI, I mean, we're looking at going back to some stuff we were doing 6-7 years ago of using OpenCog to control simple agents in a Minecraft type world, just building stuff and achieving goals, finding stuff, having social interactions. And you know, we pick Minecraft because it's open-ended. And I mean, I don't think just getting points in some video game is useful for driving work toward AGI, but I think a simple open-ended world to explore can be valuable. Microsoft worked that direction in Project Malmo, but I think you can do a lot more with that. So we're starting to play with that with the current OpenCog system and moving toward OpenCog Hyperon. And I think, while the Sophia robot with its theatrical aspect has pluses and minuses for AGI, I think humanoid robotics has a lot to be said for it, because these humanoid robots are interacting in the same physical, social, emotional world as humans are. So I'm quite interested in collaborating with Hanson Robotics on intelligent, cognitively powered humanoid robots as a test case and teaching playground for OpenCog Hyperon as it evolves. And we'll talk about that again tomorrow, where, as well as the OpenCog Hyperon sort of core AGI architecture, where a number of colleagues and I were working on a commercial project called TrueAGI, which is being split out of SingularityNET Foundation. And what TrueAGI does is it uses the OpenCog Hyperon together with some specific knowledge bases and running on SingularityNET platform for decentralized scalability. TrueAGI uses OpenCog Hyperon, specifically for control of robots and smart devices. And, I think we can get a lot of mileage out of OpenCog on the back end of robots and smart devices, and we want to do that. But we also want to focus on simpler, demonstrable applications that any open source developer or user can just download on their machine and play with, like these Minecraft type applications. So yeah, one of the reasons I wanted to organize this event together with my colleagues is to start to pull together an OpenCog community, for the next generation. I mean, we have a cool community on OpenCog Slack and on OpenCog Google group. We haven't, those of us who are involved in the core development of OpenCog have not so far really been that good at leveraging the enthusiasm of members of our community. But I think if we're going to achieve our goals of scalability, usability, and demonstrability on top of all the cool algorithm and structures that we have, we want to be pulling in efforts from the community in a much better way than we've been doing in the past. And I'm hoping this can happen in the next months, following on perhaps some of the energy we may be able to generate from this event. And I was supposed to leave time for questions, and I didn't do it. On the other hand, I did manage to get through all my slides, which was remarkable. Thanks.
Thanks, Ben. So I was wondering about the questions, because there's quite a few very interesting questions running the gamut from big vision questions to more technical, detailed questions. I think, given that we're at the front end of this event, that perhaps focusing on the bigger picture and then leaving the more technical details for later discussions might work.
Yeah. I think we can screw with our schedule a little bit, and I can take a few minutes of questions. And yeah, I agree. Highly technical questions are probably better for answering in a textual format than verbally.
Right.
Anyway, I'll take a look at YouTube comments and maybe answer some questions on there later in the morning. Have you? What high level questions?
Well, there's a set of a few high level questions that in some sense seem related to me. So one big one is whether you really think AGI is a pure emergent phenomena. Related to that, I would, in my mind at least, is kind of your notion of emotional intelligence and how that plays in. And an interesting question that kind of came up, I think we've probably discussed this at some level in the past, was Alcohol interferes with the brain's communication pathways, which affects how the brain looks and works. Can OpenCog be similarly interfered with in an ephemeral sort of way, or is it strictly bound? I think that it's combination
All right,
of
yeah, let me, so,
addressed.
I mean, as to whether AGI is a purely emergent phenomenon, that immediately made me start thinking about the simulation hypothesis and creationism, because I'm thinking of AGI as a phenomenon that's emerging out of human culture and society and human intelligence, so that what a programmer types is itself an emergent phenomenon. So I started thinking about, is our whole universe an emergent phenomenon, or was it created by a third grade programming student in some meta universe, right? But I mean, if we set aside that level of emergent phenomena, I mean, I think human intelligence has emergent aspects, and it has aspects that are wired in by our genome and our biology at birth. These may be emergent in the context of the evolutionary system that produced each of us humans, but from the standpoint of the individual, they're not emergent. They're wired in from our birth, right? And I mean, in the same way, I think the general intelligence of an AGI system is going to be an impure emergent phenomenon. Like we are wiring in some biases and some algorithms and some representations, and many others have to be learned. And I mean, I think for AGI, we don't want to be giving long lists of common sense knowledge like was done in the rule-based expert systems of the 70s and 80s. Although in the bio AI applications, we're doing that. We're feeding in the gene ontology and the structured knowledge. But yet that's very narrow AGI-ish, right? And if we want to move toward a narrow AGI biomedical system, then the nature of aging can't just be some labels in the gene ontology associated with some genes and proteins. The system has to have a grounded and emergent understanding of what aging is in organisms. So I think the knowledge has to emerge. On the other hand, can you seed the emergence of knowledge by feeding in some structured knowledge? That's a research question. And I think this gets quite deep into the atom space, is both for knowledge representation, and it's a meta-representational framework. So we have some concrete representations we're building in, like there's an inheritance link, which encapsulates the notion of logical inheritance between one node and another, like cat inherits from animal, or some node representing a concept the system learned on its own inherits from some other node representing another concept with no English name that the system invented on its own. But the notion of logical inheritance, we are wiring in. On the other hand, Alexei and his team in St. Petersburg wrote a paper a couple of years ago using machine learning to learn new logical inference rules for manipulating the truth values of these inheritance links. And we're in the OpenCog Hyperon design, we're discussing, using gradual typing for the type system on Atom Space, so that when the system invents its own new node and link types in the course of its thinking, then these can be incorporated in the system's reasoning. So I mean, we're starting with some concrete things we think are very important for general intelligence, like notions of probabilistic and fuzzy logical inheritance. But we're considering this as something that will trigger the emergence of broader intelligent processes and patterns, which then eventually can reflect back and allow even the lower level stuff that we wired in to be rewritten. And yeah, one of the design principles underlying Atomies 2.0 that we're working on is, we want self-programming and self-modifiability to be easier. I mean, you can do it in the current system, but it's awkward, and we want it to be simple. And this underlies the cogistry algorithm for computational creativity that I hinted at either. You need easy self-modification.
So I don't know if we want to go with another question or go straight
Sure,
to.
give me one more. I'll try my best to give like a short answer this time rather than explaining the entire universe.
Okay, well, maybe this one is a good transition one. So a person wants to know who's not necessarily in the field of AI, how he or she can contribute to this OpenCog success.
This is a broad question, right? I think clearly the proximal need that OpenCog project has is for folks with computer science, cognitive science, AI, software engineering background to just pitch in on designing and building the next phase. On the other hand, if we look at the notion of neuro-AGI, we're looking at potential applications in every single area of human pursuit, right? So I mean, really, no matter what area of human society you are wanting to participate in, there's going to be ways for OpenCog-based neuro-AGI systems to help out there during the next few years. So there's interesting discussions to have, but that does devolve into a very long list of potentials, because there's applications in media, in biology, in chemistry, in social work, in governance, or whatever it is. But I think yeah, we're going to need people engaged in every area of human pursuit who are interested in thinking about how to effect beneficial transformation of their area of human pursuit using narrow AGI as it emerges toward AGI. But that
And maybe this would be a good
on the OpenCog Slack or email list, because that devolves into a large number of special cases.
Right. I mean, this is kind of related, and maybe this would be a good transition. Is it possible to have a simpler, less powerful version of OpenCog that's more developer friendly, to give people more people an opportunity to join the community? The complexity can be overwhelming.
Yeah, I mean, I have thought about that a great deal, and I think that that's not as feasible as one might like it to be. I think that my hope is that once we have created the OpenCog Hyperon system that we're now in the early stages of architecting and designing, my hope is that while the inner guts of that are going to be extremely complex still, my hope is that we're able to make it extremely easy to use from the standpoint of application developers who are wanting to integrate it into applications that they're building. And I mean, a decent analogy would be your an iPhone or an Android phone. I mean, no one has figured out how to make the chip design inside an Android phone or an iPhone really easy or accessible for the average app developer to understand, let alone the average user to understand. I mean, there's a hell of a lot of wizardry inside these little devices we all carry in our pockets, yet not just for end users, but for app developers, there's evolved a brilliant ecosystem that makes it very easy to make these devices do useful and important things. So I think one can do that. I think one can design languages, frameworks, and interfaces so that leveraging OpenCog to do stuff becomes as easy as building an iPhone app. That isn't necessarily going to make crafting the inner guts of OpenCog Hyperon easy and approachable. I mean, I think that's hardcore stuff in the same way that designing the chips inside a cell phone is hardcore stuff. At least that's my thinking about it so far.
Okay, I don't know if you wanted one more or not.
No, I think we want to move on with the event, and then we will have a bunch of chances tomorrow to go into OpenCog Hyperon next generation stuff, and a couple panels which have time built in for interaction more explicitly. So thanks. Let us move on to the next victim here,
who is Mike Duncan. He's going to begin the overview for BioAI by talking about the bio atom safe. He's the chief computational biologist at Mozi AI, and his background is actually quite fascinating. He served as a physician's assistant. He's done a lot of machine learning over the years with Ben and various colleagues. So a breadth of experience from both the biology side as well as the data science side. And he's going to kind of set this, just like Ben kind of set the stage of the overall conference. Mike is going to begin setting the stage for the work we were doing in BioAI. Mike?
Hello. Can you see me?
Yes.
Yes.
All right. Here we go. Okay, so I am going to do, basically I've got like sort of 4 pieces I'm going to want to go through. Maybe a short bit on sort of putting the biomedical research in the context of the OpenCog project and SingularityNET. Then do a bit, and I mean, the topic is formally the bioatom space. So I'm going to do sort of like a biology 101 to go over kind of the biology that we're kind of putting into the atom space as a knowledge store. And hopefully it'll be, you know, that's a huge topic, and hopefully it'll be enough so people who don't have a lot of familiarity with it can just get an idea of what's going on in the context of what we're doing with OpenCog. And then I'm going to go over the current system that we have, the gene annotation service, which is a service on the SingularityNET that is our current implication or implementation of our work. And then I guess depending upon time, I can sort of go over future directions. So I guess to begin, let me get to I'm gonna have to be going back and forth between my browser and some slides, so bear with me. And share screen. Okay, so wait, is that working?
Can I help you?
Oh, there we go. No.
It's working.
Oh, here. Oh, wait, I'm confused by the delay because I'm checking that out. Okay, so.
Yeah, it's best to ignore the actual live stream. I'll be monitoring it. So maybe you can maximize this screen.
All right, I can do that. Anyway, so this is in the context of, wait, I don't want that. Okay, so I mean, I think Ben sort of mentioned neuro-AGI. So I think the best way to think about this is as, you know, we're trying to develop a system in that vein of an AGI aimed at at one narrow slice of information. And so for that would be solving biology and medicine. Now that's super ambitious, and hopefully I can sort of convince you that this is actually a reasonable thing to try to do. Actually, let me switch to the browser. Oh, I'm doing my live stream. Okay, so I mean, so I've sort of discussed this before, or actually Ben and I put out this paper on the blog post on the SingularityNET blog talking about what it means to solve medicine by implementing sort of decentralized biomedical AI on the internet, on the SingularityNET. And so that's worth reading. So maybe, let's see. Where's my notes? All right. Okay, so in this, we basically talk about, as a software design project, what we were trying to do is develop a system that can characterize sort of biological systems in general, and in particular, the human body, where if enough, information is given to the model for a single individual person from their medical records and from, lab tests, current information from wearables, then their health can be assessed, and any kind of disease can, a treatment, a disease can be diagnosed for any problems, and a treatment can be developed based on all their individualized sort of data. And so we're going to talk about that in here. Now, let me get back to here. So now, of course, we don't actually have, we don't have neuro-AGI to be able to pull this off yet. And like biological knowledge is not nearly complete enough to be able to do that. But OpenCog is evolving the AGI part, and I mean, the idea with our system is to sort of evolve in parallel with the AGI development and the development of all the biological and medical research in the world, put into an OpenCog atom space, then we can sort of achieve this goal. So, all right. And so how will that work? Okay. So what biology do we know? We know a lot of the sort of basic parts, the molecules, starting with DNA, cells, all the molecules, all the little, the biochemistry, and we know sort of the basic operating system. I mean, that's kind of like the fundamental dogma of molecular biology, which is DNA encodes RNA, which encodes proteins, which goes to build all the parts of living systems. So we just have to fill in the gaps and sort of understand how it all fits together, and we're done, right? So what that looks like in our practice is that, sort of calling the system Mozi, which is a Chinese historical mythological figure who was one of the original scientists and doctors. So, so we're sort of developing the Mozi platform is the biomedical implementation of OpenCog. And so the idea is, so we get all available biomedical knowledge into an atom space, which is the bioatom space. Now to fill in the gaps, then we just sort of like take new experimental data analyze it using OpenCog machine learning tools, generate new knowledge, add that to the database, add that to the bioatom space, generate new hypotheses based on our new discoveries, use those hypotheses to formulate new experiments, and repeat. And like you iterate that over and over again with basically, eventually the world biomedical research community, then we can get to the end goal of having a complete model of living systems and the practicable application of that to medicine. Okay, and that can be sort of split into sort of on two levels. So, I mean, you can have this working for individual researchers and their labs with their own bioatom space to hold, and that would hold, all the publicly available information, which I'll sort of get to, and, personal and proprietary data. And then they can be implemented that way. And then this can also, you can also imagine a sort of putting the bioatom space online for as a sort of Google knowledge service. And so anyone could ask questions, upload data, and contribute to the general knowledge store. All right. So now what does that look like in terms of our data? And this is sort of getting into the biology part. So, I mean, now if you're not familiar with the current state of biology, it's sort of based on, it's part of the big data and computer revolution, and how that's manifested in biology is the generation of vast quantities of data. Because, I mean, partly because there are, just living systems are so incredibly complex, and just the new technologies are generating massive amounts of data to represent that. And then from there, there's huge numbers of scientists around the world developing all that. So that information, is increasing exponentially, and no human brain can contain it. So to handle that, we need to stuff it into one universal representation. So let me see. Okay, so getting back to what we do know is in terms of the different parts, there's DNA, and which is characterized for people. There's 3 billion bases. So there's a sequence of 3 billion letters that encodes the human genome, and we can sequence of that and figure out based on a sort of general template. That's the result of the Human Genome Sequencing Project. We can, for every person, we can generate data where we can find out what their difference is from this sort of reference sequence. I mean, the average person has a million different, between any two average people, there's a million different variants, at least on average. So that's kind of part of where we're starting with. And that's just sort of the baseline. Epigenomics data is sort of the, and DNA is just there's a series of giant molecules. Epigenomics data is kind of part of the packaging system that reads that program information and basically like hides different part of it, makes it available in different cell types. So cell types can perform different functions. Then those particular stretches of DNA get translated into RNA, which is the transcriptomic level. And so we get data sets where you have from any particular experiment, from some human tissue or individual human cells, or you can get you can read the levels of transcripts of every gene in the human genome. And so that'll be different for different cell types and for different disease states. Then those RNAs, and so another slice is proteomics, where you can experiment and look at all the different kinds of proteins that exist in a single cell or samples, or a tissue sample. For all the protein molecules that are translated from the RNA. And then there's the metabolomic level, or sort of small molecules that are all the other kinds of chemicals floating around. And so each of these kind of levels are experimental technologies that produce, huge data sets from each experiment associated with each single sample. And then, any kind of study looks at many, many samples and compares them all. So, so this is sort of the experimental data that needs to be, that we're working with. All right, I don't want to go there quite yet. Now, actually, I will go here. I mean, this probably should have been before the previous slide, but so at the most basic level, getting all this kinds of information into, well, what? So this is, here, let me back up. Okay, this is kinds of experimental data. The other kind of data we have is sort of all the compiled, publicly available data that exists online. So let me show some examples of that now. Okay, so, okay, by the way, I just want to do a shout out for the Atom Space Wiki, the OpenCog Wiki. I mean, Ben has sort of referred to the atom space as the hypergraph of nodes and links that makes it up. So that's what we're trying to port all the data into. And I'm not going to go into a lot of detail of it, but the wiki page is a good source to get some background info on that. But let me actually, what I'm going to do next is show a little video. And this will sort of put all of those different types of experimental data into context, so you can sort of maybe relate it to the actual biology. So this is like, I think one of the most accurate kind of imagings of what these molecules look like. We're at the level of like DNA, RNA, proteins. So let me sort of just like play that for a minute, and maybe this will sort of like ground all the babbling I've done so far.
I would probably suggest you to mute the video to prevent any echoes.
All right, well, let me turn it, right. Actually, I'll just turn off the sound so you can still hear me, right?
Yes, perfect.
Okay, so this is DNA folded up, and now this is DNA getting turned into RNA. So those green blobs are protein machinery that makes RNAs. Now here's the RNAs going out of the nucleus. and coming out into the cell. And there's like the nucleus inside of a representative cell. Those green bits of the mitochondria, the powerhouses. So here's the DNA again, this helix, the double helix. And all that's each packed into every single cell in your body. Now there's some machinery, like this is for duplicating the DNA. Oh no, this is packaging the DNA. So to fit that giant, like a meter long string into each of your microscopic cells, there's a really complex system that organizes it and packs it all together. Again, this is all done by these molecular machinery that's a complex groups of proteins, and they bind it all together and wrap it up into these levels of spirals to pack like literally like a meter long molecule into the nucleus of every cell in your body. Okay, so these are the chromosomes. They get all folded in. This is actual cell video. So that's what it looks like when a cell is dividing. I mean, most of the time it gets packaged that way just for cell division. So the DNA is duplicated, packaged all up tightly, and then cells can be divided. And that's how you get one cell. I mean, going back to the operating system, knows, there's a whole process that can turn one cell into two and then differentiate them into multiple different kinds. Here's the machinery of DNA getting duplicated. And I believe this is real time. So you've got this kind of information processing where you're getting 2 copies from one. But again, so this is what we're trying to represent in the atom space at the most basic level. I mean, biological knowledge is a hierarchy that goes from atoms to societies and ecosystems. And all of them have to be taken into account to understand it, to understand biological systems and medicine. Right now, in our current implementation, we're just at the molecular level. But here's some of the processes we're representing. So for different things to happen, different genes need to be turned on. And this is, a representation at a very low level of what that looks like. So that spot has to be opened up. Then the transcription is done. So the DNA is getting turned into an RNA template. So from the main menu, we get like one recipe out from the main cookbook. And this is machinery that's all made of component little proteins. And I mean, this is happening like, thousands or tens of thousands of instances can be taking place of this in each cell all the time. So that's just the code. And each 3 of these amino acids in a sequence maps to one amino acid in a protein. Okay, now this is the DNA wrapped around a packaging protein, and this is where epigenomic data is encoded, where you can decide where like those molecules determine if the DNA is open and ready for transcription like that. And here's, some of the machinery, like deciding which genes to turn off, by exposing them for transcription. And, the molecules that it gets wrapped up in, get tagged by other proteins, and that turns them on or off. And this is, again, the DNA getting opened up. All right. And then the last bit. I mean, here's inactive DNA. So, again, all the genes for all the different types of cells for everything are in every cell, but different types of cells only need certain kinds of genes. So, they get turned off. And, what decides that, again, is epigenomic information. And that's determined by, all these other proteins, and experiments can determine on a, whole genome level which ones are active and which ones are not. And there's actually many sort of levels to that. All right, so hopefully, let me get out of there. And so I just wanted to show that just to get, to ground, what we're talking about here. But in terms of other publicly available data, that's a representation of what we're trying to stuff into the atom space. But, what does the rest of that look like? And this is just an example of all the different kinds of just publicly available biological data. And, this is just, each link is a whole database, which can have, hundreds or tens of thousands or millions of entries. And I'll get into that in more detail about, just based on what our system is. But let me go back to here now. Oops. And let me get, okay, so at the most basic level, all of the information going into the atom space is based on sort of like we've broken it down into two kind of types of knowledge. There's conceptual knowledge, which is all the ideas about what's going on that we have. And so we have a specific form of concept node called a gene node. And then there's all the experimental data, which is another type of concept node that we specifically defined as molecule nodes. Now, and the molecule nodes, again, go back and represent actual molecules, physical objects, proteins, pieces of DNA, small molecules, drug molecules. And so this is how all these different kinds of experiments get represented, all these kinds of omics experiments. That data gets represented as a molecule node. And now and then gene nodes, I mean, there's also, I mean, this might sound weird at first, but genes are actually concepts. I mean, there's not really a gene you can point to, except maybe, you consider a particular stretch of DNA, but that's kind of an arbitrary boundary that we've created. And it's sort of related to how it functions and how it interacts with all the mechanisms of the cell to make the cell work. So we have those separately. And then, we also have, and I guess this is sort of the different levels. And the ones that are checked are ones we actually have represented so far: molecule, subcellular systems, and cells. And let me just get actually back from this. Okay, so there's all these databases of just sort of like physical entities, catalogs of proteins, catalogs of small molecules, catalogs of phenotypes. And there's also more conceptual knowledge. I mean, Ben was referring to the gene ontology. And there are actually like huge numbers of these, actually. And this is a whole database of just, these are all ontologies, which are kind of structured data that's machine readable. And so this is sort of like actually kind of a bridge to generally intelligent systems. We can sort of codify concepts. You know, Ben was talking about these lists of rules. And there's biologists have made huge numbers of these that we can exploit. That's basically sort of like a midway step between like sort of just natural language concepts and more symbolic representations that we can deal with our current algorithms, our current AI algorithms. And those are just can be represented just as more general concept nodes in our current representation of the bioatom space. So let me see if all right, so all right. Now I apologize for being kind of scattered. Right? This is sort of at the last minute and it covers a lot of stuff, but maybe somebody who's on the call can just give me a little feedback on how much sense this makes for background. And let me see if there's any more biology that I want to talk about.
Yeah, Mike,
Actually,
since you asked, I think it will be interesting to look at a few specific examples of atom space knowledge representations
Right.
of
Okay, yeah, no, so I'll just switch, I guess,
knowledge.
I'll switch to actually giving an example of what we're actually doing now. So
Yeah, like just show what are some of the specific node and link constructs in atom space that we're using to represent some of the knowledge from these databases, because that's where the rubber hits the road, right? And that will tie in with what Nil is going to talk about using reasoning on these node and link constructs in atom space representing this biological knowledge.
all right, so yeah, so let me pivot to like what our concrete work is, and hopefully that's enough biology to help you like for it to make sense. Okay, so what we have currently is the gene annotation system, which is implemented on the SingularityNET. And wait, let me get to my. Okay, so again, so now all of biological knowledge is as a huge hierarchy. We've sort of gotten this level so far, and what that looks like is that we have. So what the system is that we have, the actual working software system, is the gene annotation system. So you can take a list of genes, and that's basically a query of our bioatom space on what the associated gene ontology terms are for that, what biological pathways it's associated with from a particular database, and what molecules, what proteins, these genes are known to interact with from experimental and living system data. And that looks like this. All right, now I've got to switch to the other computer. Okay, so if you looked at our, if you went to SingularityNet and looked at the gene annotation service, or if you downloaded from our GitHub repos, this is all open source, so you could actually download these, and I can show you that, or probably will. This will all get links will be added to the YouTube file eventually. But so what you do is you can put in genes here. And we use the gene symbols. So so you'd enter a bunch of genes, or you can have a text file list. And then you choose the annotations you want to use. Say we want the gene ontology. Now that has three actually sort of separate components, which are biological processes, which is kind of like biological functions, which is kind of like what a gene is. Genes are types of functions, really. But there's sort of these process concepts. There's cellular components, which sort of locates genes inside cells into particular subcellular structures, or there's molecular functions. So that's looking at proteins as molecules and sort of pieces of them, how they interact with other proteins, other molecules, how they fold. Then there's pathway databases. Actually, on the SingularityNet, we only have the Reactome. You can access another version, some more complex ones. And you can choose to also include small molecules, which is drugs, metabolites, sugars, fats, besides proteins. Cross annotation allows you to get, BioGrid is the interactions. Now, when you get a path, when you annotate with a pathway, what that does is it pulls up a pathway that the gene you select is inside of, and it might be part of it includes other kinds of other proteins. So by cross annotating, you can also pull up the connections. If you select the BioGrid, that just gives you the interactions between the proteins that you input. But if you do the cross annotation, that gives you back all the proteins that are associated with that gene in that pathway. And this will also let you pull up the interactions between them from the BioGrid. You can also get different kinds of RNA that are associated with the proteins or genes. And you can look at it at the gene level or the protein level. And we actually threw in some SARS proteins. So what does that look like? Here I've got some pre-done examples. Let me just actually go back. So say I'd put in a list of genes, and this is what the result screen looks like. So these are the input genes that it's put in, and these are actually the SARS-2 virus genes, or their proteins. And the BioGrid had just published those a couple months ago, so we wanted to include that just to give an idea of how things are more relevant. And so what we did was cross-annotated that, or Now, so this is what it found in the output. So it found these are all the genes that were found to be associated with it, with all those proteins. Now there's many of them. And they can all be searched through. And they can also be downloaded. Oh, we don't want that out of the way. And you can also get the scheme file. So now this is what they look like. So here's the pathway annotations. So well, actually, before I get that, it'll make more sense if you see the actual visualization. So let me go back to that.
Hey, Mike, I'm just conscious of time. I think we have like 5 more minutes that we can go on for.
All right. Well, anyway, here's the visualization of these things. These are the proteins. And all right, I don't have time to get into the functionality, unfortunately, about what you can do with these, but you can pull up all the information from the source database. And if you go back and look at the scheme files, that looks like this. So let me share this part. Okay, so this is sort of the scheme code of the results that you get. So this is just sort of the gene nodes, and sort of like these are the symbols. This is there's human level, like human readable names for them, location information. That's used actually we have a cellular visualizer as part of that's a separate part of the service in development now. But then here's an example of annotations to the Go ontology. So we've got this one gene node here, say, is related to, so it's got this tag in the database. And this is it's a biological process. So that's which Go ontology it's from. And its text name is regulation of extracellular matrix disassembly. So there's a concept that categorizes that. Now, let's see if we can I'll just get an example of some of the other kinds of Go cellular component. There's the kinesin complex. So this particular protein is part of the kinesin complex. And then say a molecular function. There we go. Actin binding. So this particular protein, this gene node, its protein binds to actin. So that's just an example of all the conceptual information that you can get. And then pathways. So this gene is part of this pathway, which is the keratin type 1 pathway. And this is where it's located. So that's what the information looks like in the scheme. And All right, so maybe just to wrap up, switch back to here. Okay, we've got for the current system. This is what our cell visualizer looks like, or the newest version. It's in progress. So you can actually visualize the proteins that you're getting back inside cells and the links between them, and have access to all the information. And so I guess I'm out of time, so I guess I'll wrap up there and at least let people ask questions so we can sort of fill out all the stuff that I missed.
Thanks, Mike. We have time for questions, or should we move on?
I think we're a bit behind schedule, so perhaps we can move on. And if people are interested, they can just let us know in a community chat, and we might be able to revisit this topic later as well.
Okay. So thanks for that, Mike, and giving some background on the bioatom space and how it can be used. Next up, we have Deborah Duong and Manhin Luan. And Deborah is another fascinating individual, been working in various different projects with Ben for decades. I don't even remember the first instance of that. And then Manhin is out of Hong Kong, and he'll be following up on the second half of this talk. And they're going to be, so Ben mentioned at the beginning in his keynote, kind of connecting neuro-symbolic, and kind of some of the keys for making that work are our current work is through neural graph embeddings, and Deborah and Manhin are going to be discussing some of those neural graph embeddings on the bioatom space. Deborah?
Thank you. Okay, let me try to share my screen. Here we go. Can everybody see my screen?
Yes.
Wonderful. And okay, here is the beginning of my talk. Well, I'm going to do half of the talk, and I'm going to talk about our neuro-graph embeddings, and then Manhin's going to come in and talk about some ways to look at the quality of these and have it help inference. So first of all, we're going to look at what an embedding is. Now, an embedding is actually an extraction from the early layers of neural networks. Neural networks typically take a larger vector as the raw input, and then they output a smaller vector of the data as an answer. Okay. In order, can you still see my screen? Because I see myself, but I don't see my screen.
Yes, we can.
Yes.
You can. Okay. I'm not going to worry about that then. All right. In order to get a correct answer, the network typically creates a more compact version of the input. And in order to get that more compact version, it has to get more abstract in order to answer the question that the neural network is asking. And so those middle nodes of the neural network represent those abstractions. Well, on the way to those abstractions, you have to take that possibly very, very long input and compact it. And that compaction contains some of the first abstractions made. That's called the embedding layer. the very first layer of the neural network. And we use the ideas from natural language processing neural networks to inspire us. And we have used the embeddings from natural language processing to describe our biological space as well. So let's look at NLP embedding for a second. So the input layer is really, really long, typically as many words as there are in the English language. And then the second layer that compacts those words is of any size you tell it to, and like 100 or 200 is kind of a typical size. So we've gone from, you know, hundreds of thousands to down to 100. So that's a very compact mapping. And then all of those words have their own vector of 100 floats that represents the one word. So each one is now mapped into a vector of 100 floats. So you can see it's a reduced dimensionality representation, but this has some special qualities in that each word is closer to the words that are similar to it and farther from the words that are different to it. And so this similarity mapping holds knowledge that can be used in different computations than the original, such as the symbolic computations in the bioatom space. Okay, so here we see an example of word-to-vec embeddings. And what they take as input is they take sentences, and those training samples are created so that you can predict a word based on its context. For example, the quick brown fox jump over the lazy dog. A window is passed over the sentence, and then the word that the net is supposed to predict, in this case, is given examples of the context. This is called the skipgram. And skipgram is based on, in NLP, what's called a distributional hypothesis, that words that occur in the same context have similar meanings. Okay, so why do we care about NLP? Because the higher order co-occurrences of words are used in the neural net to predict the word by its context. And those higher order co-occurrences are holistic and give meaning to the words. And we want to find the same kind of meaning in the bioatom space. Okay, and so once those embeddings are created, we can map them out and look at them, and we can see that different directions now have a meaning. And I don't know if you're familiar with the famous, queen minus king equals woman minus man, but that implies a direction of meaning, that as you go in the same direction in the space, you get a similar meaning. And you can do an analogy, like Moscow is to Russia as Ankara is to Turkey. So here, because we're humans, we can only see in 2 or 3 dimensions. We've taken those 100 dimensions and reduced them down again to 2 or 3 dimensions just so we can see these relationships. Okay, so now we want to get that same meaning through holistic context and higher order co-occurrence in our biology space as well, and then use that to help us with our inference. And so here's a picture I found in another person's work that uses a lot of different biological ontologies, just as we do. And what we want to do is we want to find a line, in fact, an inference line that goes from one type of thing to another that will help us discover things like different drugs to use. Okay, so this line corresponds to a sentence, right? And the sentence in a graph would be generated by deep walk. So we generate sentences from our graph, and then we take them and we put them into the word-to-vec I just showed you. Except we've taken existing deep walk work and we've modified it to our bioatom space, which is a weighted relational hypograph. which is different from other ontologies that deep walk has been used on in the past. Okay, so Perosi et al. Created the deep walk algorithm in the first place. And what he just did is use random walks on graphs. You know, take a random initial node and then look at how many links that this initial node connected to and randomly take one of them and get to another node and then randomly take the links on that, so on and so forth, to make a sentence as long as you specify, right? And then Ashashani took this deep walk and used it in biological graphs. In fact, RDF triplets, which are the basis of all the ontologies you've seen. Now, we adapt this, this algorithm to our weighted relational hypergraph. And the difference in his algorithm, he takes a random node and then takes a link randomly and then a node randomly, just as in the original deep walk. And the relations are, you know, the names of those nodes and links. And the difference we have is he has a directionality which he takes along the paths, and we include the reverse directionality as well. He doesn't have hypergraphs, so he has only triplets like link, node, link, node, but we have links to links. So we have longer phrases. You know, he has 3-word phrases in his sentence, and we can have 5-word phrases. And also he does not normalize. And so we want to be able to look at data which is unbalanced or underdetermined, and because we're specifically interested in supercentenarians who lived over 105 years, and we want to look at data from only 27 persons. So in order to do this, we've, instead of taking the random links coming out of a node, we've typed them and say, well, I want to make sure, you know, I have as much chance of going down a supercentenarian's type of SMP as I do a normal person's, even though there are way fewer supercentenarians than normal persons. Okay, so those are the changes that we have made. And so let's take a look at what that looks like. Our hyperlinks represent with 5 tuples or longer phrases. For example, here's an example to make it clear to you. A 5-tuple might be gene 1, and then a word is in location 25 in context of pathway 32. So the context would be the hyperlink on a link, right? But we need 5 words to represent this. And we also include the reverse tuple. The pathway 32 is the context where location 25 has gene 1. Sorry for the typo. Okay, so as we walk along the graph, we can see, you know, here I've told it, go 10 deep, or I don't even know how this is, 20 words deep, or anyway, but you can see that it can just keep going. And so we can say the supercentenarian 15 is a member of the super C class. And then that super C class has a member who is the other supercentenarian. And he has expressed the SNP here. And there's 38,000 of those, right? But this is also expressed in another supercentenarian who's expressed another SNP, and that's expressed by gene, okay? And that's in the gene ontology. And that gene ontology term is inherited by another one, which inherits another term, which has a gene ontology member. Okay, so it's kind of like it's got ADHD, right? But it is traversing the graph in a semi-random way, but including types. So we make sure we get the information that we're interested in. Okay, so Also, we have weightings, right? Their graphs aren't weighted, but ours are. And ours are weighted according to type. We've got 2 times of truth values to weight facts by: strength and certainty, right? Our deep walk represents unusual strength values with a fuzzy modifier, like this weakly, this strongly implies, this weakly implies, which we can take randomized control data and find those values, right? And we also have certainties on those strengths, right? And those certainties are represented by having a proportionate chance of going through a fact based on its certainty. Like if it's unlikely, it's also unlikely to traverse that fact, right? So the facts that we're more sure of show up more in our answers. This normalization that we have, you know, that we take type into account and not just amount, maximizes the value for our underdetermined data. Okay, so let's take an instance of the use of this algorithm, our use on supercentenarian data. Okay, so we use Clemens supercentenarian set, which had 27 persons in it, and there are 38,000 SMPs, right? And then we compare that to 503 European controls from the 1000 Genomes Project with their SNPs, both unbalanced and underdetermined. And why did we choose those 38,000 SMPs? Because those are the ones related to longevity. In particular, in a study by Timmons et al., they were related to a gene switch. And they were found to be something that correlate really closely with age before the gene switch activates, and then that correlation is lost after the gene switch activates. And that gene switch happens around age 60, so it's called the aging switch. Okay, so we took each of those supercentenarians and we linked it to a node super C, right? And then we linked those normals to a node normal, okay. And then we didn't start our walk randomly as they did, you know, in the other studies, but we started all of them at super C to make sure the net uses knowledge from the super C. Because if you start them randomly, you know, it's going to have a less focus on that. And the reason why this is a good thing is because you can focus in on salient areas. Of course, you can be objective and start randomly as well, right? But if you want to, you know, map out what you're more interested in, you start out in a particular kind of place. Here, super C. And note that we also had to make our walks longer because we had to get out of this focused area into the wider objective space, right? And to get out of that area, we need longer walks. Okay, so this is a picture of our embeddings from the supercentenarian data set. They're colored, and you can see that colored kind of goes together. So we'll specifically look at areas of this space. Okay, to find whether this is a good space or not, we look at, do we expect some concepts to be close to other concepts that we know to be close to each other, but we didn't tell the net, right? And one concept we put in is a concept of cytosol. I'm not a biologist, but I know it has to do with membranes. And when we put this concept in, we got back the closest 10 nodes in the embedding also have to do with membranes, right? So we say, okay, it's beginning to look good. Okay, next, when we put in the phrase super C, that all the supercentenarians are linked by, we get the SMPs that are most closely associated and uniquely associated with supercentenarians without having told the space this information. And those are these 5 SNPs. So that's another way we know it's a good space. And what we have here is a space that's both good at supercentenarians, which is hard to get because the data is unbalanced, right? And it's hard for your neural net to learn things in very unbalanced data, but it's also good generally, right? It's also got, you know, cytosol, which everybody has, right? It's also got that down. So we have the desired space that maps what's closer to what you want more specifically, but then also maps what's farther away. And our hope is that we can go and get that path that we're looking for that goes from the specific thing we're looking for through the general facts to find out more information about what it is that makes a supercentenarian a supercentenarian. Okay, so now I'm going to hand it over to Manhin, because he's got other ways, other arithmetic to use to find additional measures of quality of the embedding space. Ibby?
Yes, one moment. Let's see.
Oh, does anyone have any questions, or do we, I guess we have 2 minutes.
Yeah, so actually Dave asked, Word2Vec uses a vector space to store all embeddings. Do you have the same thing in the bio-atom space? Do you have to retrain your model for the embeddings every time that you add new information?
That's a good point. But embeddings are something that you can increment on as well as retrain, right? So if we got a lot of new information, we might want to retrain them. But if we got a little information, then you can add to an embedding. And not just Word2Vec, but also embeddings like transformers. These are known as something that can be applied from one domain to another without recomputing the whole thing. So you can find embeddings, you know, online and then modify them, add another layer to get your individual question answered. So they can be incrementally improved as well as recomputed.
Awesome, thank you. Then one more from Predrag Radovic. What kind of lifestyle choices impact longevity gene switch?
That is a good question. And this is the kind of thing we're trying to answer, right? We're trying to, because we have a bioatom space that has a lot of information in it, and we don't have to just include gene information. We can include gene expression data information that is a result of our choices, right? Which genes get expressed is a result of our choices as well. So this is something we are actively studying. We have that gene expression data in our bioatom space as well. I do not know the specific answer to your question yet, but we're looking for it.
Awesome, thank you very much. Let's see, Matthew.
Yes. Is Monhin?
Yeah, so let me start sharing the screen. Oh, okay.
Cool.
Okay, so I'm using the screen now.
Yes.
Okay, awesome. So yeah, thank you, Debbie. And this is a continuation of the presentation. So as you can see, we got some interesting results by using the deep walk algorithm, which is sort of interesting because we kind of, it kind of repurposed the Word2Vec model to instead of creating vectors for the words of the sentences, we create vectors for the nodes in graphs. So in the way to label hypergraph in our case.
Sorry to interrupt, Manhan. Can you please check your microphone, because there seems to be a sort of echo.
Mm. Is it better now or?
That's pretty much the same.
Let's see. Well,
Sounds better already.
oh, it is better already? Okay.
Yeah,
Okay.
very good. Thank you.
All right. Let me try again. Okay, so it is better, right? Since we have like some vectors built by using the deep walk algorithm for the nodes in our hypergraph in atom space. So another direction that we are looking at is to see if there is an actual correspondence between the embedding vector space and our symbolic space. So specifically, what we are trying to do is to see if there is a when we do the vector arithmetic operations, we want to see if that would align with the semantic difference between concepts. So this is what I'm going to talk about here. So in the context of bio AI, one relevant measure of the semantic difference is what we call the intentional difference, which is handled by our logic engine called the probabilistic neural network, or PLN in OpenCog. So basically, this is the main component being used for handling uncertain inference in OpenCog. So and in intentional reasoning, it concerns only the properties associated with the concept. And for each concept, I mean, depending on the data set we're using, we have a set of properties associated with it. Or more precisely, it would be a fuzzy set of properties associated with it. So the degree to which a property P belongs to the fuzzy set of properties of a concept C is calculated as the amount of information that is given about a member of the concept C by specifying the property P. Or simply speaking, it is roughly like the weight of the property denotes like how much information it gives about a concept that it links to. So in intentional reasoning, there are a number of operations that we can do, and as I said, like one of which that we have been playing with is to compare the difference between concepts, which is what we call the intentional difference, and which can be defined as the difference between the fuzzy set of properties of the concept A and the fuzzy set of properties of the concept B. And so in order to calculate the intentional difference between two concepts, like there are a few steps and there are a few key atoms involved in the process. So first of all, we have a concept node, and of course this is a kind of node that we use to represent concepts, to represent any concepts. Basically, it could be like dog, a cat, or a computer, a headphone, etc. And the atoms or other concepts that link to that particular concept can potentially be considered as a property of it, but of course it depends on like how they are linked together as well, because there's a semantic meanings for each of their atom representation. So then we have the subset link, which kind of denotes the extensional inheritance relationship between two concepts. So for example, if we can have a subset link between the concept cat and the concept animal. Yeah, so, or in general, if we have a subset link between the concept A and the concept B, then its true values denotes a conditional probability of B given A. So that is a subset link. So once we have all these probabilities between different concepts in the atom space, we can then find the attractions between them, which are represented using attraction link. So for example, if we have an attraction link between the concept A and the concept B, then its true value is calculated as the probability of B given A minus the probability of B given not A. So, or in other words, it is kind of telling us that if B is more likely to be a property of an element of A than an element of not A. So this is kind of like a rough measure of the attractions. And once we have this as well, we can then calculate the intentional difference between concepts and represent it using the intentional difference in the OpenCog atom space. So again, if we have an intentional difference link between the concept A and concept B, then its true values is kind of reflecting the fuzzy probability of A having a property that B doesn't have. So this is like a rough sketch of how the intentional difference is calculated in OpenCog. And from here, we also did several experiments, and one of which used an atom space filled with data about actions taken by students on a popular boot platform, a massive open online courses platform. So we use this data set because of its nature and its simplicity. And from it, we want to see if there is a correspondence between the nodes representing students attending the mood classes and their corresponding vectors built by the deep walk algorithm. So the assumption is that if like two nodes are semantically or geometrically similar to each other, then their embedding vectors constructed by the deep walk algorithm should also be similar as well. So here's the result on the slide. So basically, each dot on the graph represents a pair of students who attend a mood class. So the x-axis is the intentional difference between the nodes corresponding to the pair of students, and the y-axis is the vector distance between the vectors for the nodes corresponding to the same pair of students. So as we can see, as the intentional difference approaches 1, which means there are no or close to no common properties between the pair of students, then the vector distance tend to be larger as well, and vice versa. As the intentional difference is smaller, the vector distance will also be smaller. So there is a clear linear correlation between the two, which sort of tells us that this methodology works. So there is actually a correspondence between the two under certain conditions. So then we also ran another experiment using the same method but a different atom space. And now we have a bio atom space filled with the gene ontology data. So as you may recall from Mike's presentation, the gene ontology data, like this contains like a bunch of gene ontology terms, which could be like some mitochondrion or amino acid binding, etc. And they all falls into one of the three domains, like the cellular components or biological process or like molecular functions, etc. So anyway, so here instead of comparing the nodes representing mood students, we use the nodes that represent gene ontology terms. So again, each dot here is a pair of a gene ontology term, and the x-axis is the intentional difference between the pair, and the y-axis is the vector distance between the same pair of the gene ontology terms. So from this graph, we can also see a very fake linear correlation between the vector distance and the intentional difference. Although the correlation shown in this graph doesn't really look as good as the previous one, but like biological data is usually a little more noisy and messy than others. So I mean, at the moment, we are still exploring and trying to improve it. And we are actively looking to apply it more broadly to different contexts without sacrificing like generality. And then another thing, as Debbie also mentioned, is that we are also exploring to see if there is a correspondence between the embedding space and the symbolic logical space when we do this sort of arithmetic operation. So what I'm talking about here is shown on the slide. So basically, VA is a vector for a concept node A, and BB is the vector from the concept node B, and so on. So this kind of operation is similar to the classic example, like king minus man equals queen minus woman. So in this case, so yeah, basically we want to see if we have if this sort of vector arithmetic operation actually aligned with the intentional differences between the same set of concepts involved. So as we explore a little further, we indeed found some interesting results between the two in the same bioatom space with the gene ontology data. So one example is shown here, which is about the like T cell, B cell differentiation and proliferation. So again, this BP stands for B cell proliferation, which is a gene ontology term with the same name. So so basically, when B cell proliferation minus T cell proliferation is equal to B cell differentiation and T cell differentiation, I mean, we also see the alignment with our logical space, which is the intentional difference between B cell proliferation and T cell proliferations, and the B cell differentiation and T cell differentiation. So, I mean, this is sort of another measure, as Debbie mentioned, that this is another measure of the quality of the vector space. I mean, this is not just some coincidence or arbitrary correspondence, because this is actually based on like how we train the data. We use a deep walk algorithm. We walk through the graphs, and then we build a sequence and train the word-to-vec model. So I mean, this is the vectors are somewhat like a compact representation of all the properties associated with a particular concept node. So but anyway, this is still an ongoing research, and these sort of operations and correspondence holds in some cases, but not all. So we are still trying to see like when does it hold and like how to characterize it and see what can be improved. So yeah, anyway, so all these are very interesting preliminary results. If things goes well, there could be many potential applications of it. So one that we are currently looking into is to use it to guide inference. So for example, if you want to know like why the mutation of these 3 particular genes in person X would cause an early onset Alzheimer's disease, or like why this particular drug can cure the disease for this particular person, etc. So in order to answer these questions, we have to do like some sort of reasoning to figure it out. But like doing this kind of reasoning could sometimes be very costly, and like there could be a lot to explore for the like reasoning engine, and it may sometimes cause a combinatorial explosion. So one thing we can do here is again to do the better embeddings for the premises and the further embeddings for the conclusion using the deep walk algorithm. And then we can sort of like draw an arrow between the two, between the embeddings of the two, and then we can see like what loops or what vectors like along that line can be found, and those vectors can then be mapped back into the symbolic representations and use them as the suggestions to like to the logic engine as the intermediate inference step. So in that case, the engine would have like less to explore, and in order to draw the conclusion. Or one can also do the reverse, like use the symbolic logical reasoning to guide the vector-based AI. So I mean, these sort of things can be considered as what Ben mentioned earlier as a type of cognitive synergy between the symbolic and the subsymbolic AI. So, and this is only possible if they can access and like make sense of each other's internal representation. So like with this sort of method, that means we can potentially get the benefits of the two, and yeah, in order to build a more robust AI. So yeah, that's the end of my presentation. Thank you.
Thanks, Monhen. And thanks for staying up. What is it, 1:40 a.m. now in Hong Kong?
Yeah.
Yeah. So there is one question, but I can't, but it doesn't refer. So the back, there's a question, how is each pair chosen? I can't recall exactly what that was referring to.
Oh, maybe the pair of either students or the gene ontology term.
I think so, yeah.
Yeah, we chose it kind of randomly, really.
Okay. So interesting, you brought up the cognitive synergy at the end between the neural and the symbolic. Could you go into that a little bit more again, exactly what you were meaning there?
Oh, yeah, the kind of cognitive synergy. So similar to what Ben also mentioned. So if, for example, if the reasoning engine gets stuck at some point of the reasoning process because there are just basically too much to handle, then we can use these kind of like vector embeddings. We try to turn the knowledge graph into vectors, and then we like draw the line between the premises and the conclusion, and then make suggestions for the logic engine to to explore as the intermediate reasoning step. So that is one sort of cognitive synergy. That is like when
okay,
one
so
AI component gets stuck, and then the other can help to unstuck it.
right, so you're thinking of the embeddings then as helping. You think you mentioned it as helping guide the actual PLN, for example.
Right, and it goes in both directions, right? Because
Right.
we've already done some inference in the Adam space to create the nodes and links that are used in the deep walk that generates the embeddings, right? So inference helps generate more nodes and links and adjust the weights of nodes and links in Adam space. That helps create the embedding vectors. Then you can use the geometry in the embedding vector space to help simplify inference control. And so you have a feedback between
Right.
the processes that are most natural on the graph side, which is logical inference, and the properties most natural on the vector side, which in this case is finding a direction. But I mean, it could be other things on the vector side also.
Okay, great. So I don't think any more questions popped up.
There was a question of, do we have to rebuild the embeddings every time the atom space is
Deborah, I thought Deborah answered.
Oh, did she? Okay, I missed that. Cool.
Correct me if I'm wrong, Debbie.
She did.
Yes, I did.
Okay. Yeah, that was from earlier, and I think that's that was great, Debbie and Manhen, and Manhen, you can go to sleep now, I guess.
Thank you. Well, I missed a lot of interesting things, and
or stay up for Linus's
recording
keynote in a bit. So next up is Nil. Is he on the Zoom yet, Ibby?
Yes.
Yes, okay. And I don't know what to say, Nil. I've been working together, another person with Ben's team for, I can't even recall how many years. And another.
I think Nil is since 2008 or 9. I guess it's been.
Well, I know he was there at the beginning of Kong. I thought it was before that. He was.
Yeah, I think you're right. It probably was before that. It's back in the dim recesses of the 2005 or 6 or something. Then yeah, that's right. And it was interesting because back then around 2006 or 7, Nil reviewed the OpenCog architecture and all the ideas we had, and he's like, well, this will work. This will lead to human level AGI, but it might take us 20 years to get all the details right. And I'm not sure Nil has updated his time estimate since then. We're actually approaching his 20-year mark, and we're kind of getting there. So, but the admirable thing is that didn't put him off. Like Nil had the patience to like, all right, if it takes 20 years to figure it all out and build a few versions, I mean, cool. Like that's the way to spend your life, building the successor to human intelligence. So it's been a fantastic collaboration.
With that,
you sound very interesting, Nil, as if your voice is very squeaky. It seems to be a little bug. Maybe something's wrong with your mic.
Like a lot of helium.
Sounds kind of funny. No.
No, you really sound like Mickey Mouse on Adderall or something. Yeah.
It's like up several octaves.
Yes, I really cannot say what you're saying. No, can can you just type what you're saying? Because we cannot really understand you. Sorry. Maybe if you, do you have a mic just on your computer or laptop without the headset? Perhaps the headset is causing it.
Tim suggests he needs to change his bit rate.
Maybe we can just change the bit rate of the rest of the universe to match no.
I was gonna ask Nil to begin maybe by seeing if he's updated his time frame.
Or no,
then-
what if you
Logic.
if you talk very low, then maybe it'll come out sounding normal.
Maybe he's trying to speed everything up.
Yeah.
Speed up the singularity.
Yeah, but in seriousness, this this sound doesn't work. Let's take another minute or two to try to fix it, and if not, if I could perhaps get started in a couple minutes and start going through your deck while you fix your microphone, because I sort of I'm familiar also.
Sounds good. Neil, I'll send you a message on Slack in the meantime.
You still sound like Mickey Mouse, yeah.
Maybe restart your computer. I don't know. Now he's muted.
No, Neil, can you maybe leave the Zoom room and rejoin again, please? And before you enter the room, just test the mic.
Can you hear me now?
Yes.
Yes.
Fantastic.
Yes. Beautiful.
How's the sound?
Sound
now
is
it's really good.
amazing.
Good.
Sound
Sounds like you.
fully human.
Because I'm actually using a headphone as a microphone.
That's a good decision.
Okay.
All right. No, you sound sound even more human than your real self. It's perfect.
Okay, well, that's great. Okay, so now, okay, I'm gonna share my screen. Okay, let me just. just a second. Zoom doesn't. Okay, that should be ready to go. Okay. All right. Okay. So you see my screen, you hear my voice.
Yes, ready,
Everything
set,
is fine.
go.
Great. Okay, so I'm going to present some work with that has to do with learning over the bioatom space that Mike presented. So, okay, first of all, I mean, I just have a few slides explaining why we want to do reasoning. And there are many reasons, but in particular, one which is very interesting to me is that when you do reasoning, you can basically use background knowledge as extra indirect evidence. So basically, instead of just limiting yourself with a table with observations and trying to relate inputs and outputs, if you have background knowledge, then you can just demultiply the number of observations that you have with this indirect evidence associated with this knowledge. And in my opinion, this is probably the best way to overcome overfitting, which is really, I mean, perhaps the hardest problem with machine learning. So, okay, one might ask, okay, you're dealing with biological data. It's just particles interacting with each other, molecules interacting with each other. What about simulation? You make a simulation, then you can answer everything you want. And in principle, perhaps, I mean, it might be difficult to set the initial state of the simulation, but the problem is that even if you can do that, in practice, it's just impossible. It's intractable. And so in order to make this thing tractable, you actually need to make abstractions. I mean, you need to just take all the collective behavior of, I don't know, molecules, whatever you have, and just extract patterns that are going to allow you to, instead of manipulating millions of entities, to manipulate only a few entities and still to be able to do decent predictions. And so for that, reasoning is very handy. Okay, another reason is that reasoning can help learning. And in fact, there's an interesting positive loop here. Reasoning helps learning, learning helps reasoning. In fact, learning and reasoning are probably two different sides of the same coin. Okay, let me go to the meat of the presentation. So what we have done over the atom space, the bioatom space so far. So Debbie has been running some program evolution learning with a in-house program learner called Moses. She has I mean, before her, many people have tried that, and I mean that's already a good thing to create abstraction and to create predictive models. On top of that, so since I started to be involved in the project 6 months ago, so I started experimenting with the pattern miner. So we've got a large we've got the bioatom space, which is populating with millions of atoms, and we want to extract patterns. So this goes back to what I was saying. I mean, extracting pattern, extracting abstractions is crucial if you want to be able to do prediction in a tractable way. So I've tried reasoning as well. with the PLN that Manhin has presented a little bit. Okay, I'm gonna just explain what I've got so far. So let me recall the kind of knowledge that we have. So if you see my mouse cursor, so we have knowledge, as Mike say, from different databases. So this, for instance, is from Go, the gene ontology. So we've got that this category, which I think is about mitochondria, inherits from this category, which I think is about organelle. So it tells, well, the obvious, that a mitochondria is a mitochondrion is a specialized organelle. From BioGrid, we have things like that, such as two gene interact. From Reactome, we have things like that, where some gene is located in some places. SMP is small molecule pathways. So, well, that says that this gene is part of this pathway. And so what we want, ideally, is to just combine all these databases and to reason across them. So how do we do that? So first of all, we can do a bunch of pre-processing. So actually, the pre-processing is itself a form of reasoning. So here, for instance, we have a Go category, and we can just apply reasoning to calculate its truth value, which is going to be, well, the first number is going to be essentially the probability. So how big is this category? The second number is going to be the confidence, so how much confidence we are regarding this probability, the first number. We can do the same with, for instance, relationships between Go categories. So here, for instance, we have that this Go category, well, is a subset of this one. And here we have a probability of 1 and a confidence of 1 because it's true by definition. And we have other situations where we know we know the truth value of the relationship by observations. And so in this case, well, we can fill whatever number we get by observation and confidence accordingly. And we have more exotic links like attraction links that Manhin was presented that are useful for intentional reasoning. So, okay, in case it wasn't very clear what is intentional reasoning, it's like extensional reasoning, but you're using patterns or properties instead of elements. Okay, so what did we try? So first we tried the pattern miner. So here we have a pattern that involves two different databases, Go and SMP. And so this thing here is some atomist code. I mean, well, when I say atomist code, just understand that it's knowledge that lives in the atom space, but we call that code because it's actually something that you can run. And what it says is that the following pattern, so that the co-occurrence of this pathway and this Go category is surprisingly well, surprisingly often. So what it says is that basically they have a lot of genes in common, and it's basically it's surprising in the sense that it deviates from what it would be if we were to assume some independence. Okay, so now once we have that, so the present link is just to say that it's present in the atom space, but you can think of it as a conjunction. We can turn this conjunction into, for instance, a subset relationship. So here it is. And so once we have this subset relationship, just in one go, in one inference step, or maybe a few inference steps, we can just use that knowledge that has been packed into this one single relationship to infer new things. So it allows us to shortcut basically the abundance of data. And so here's an example. So actually the inference I'm going to show doesn't make use of that sort of patterns, but it's still complicated enough. And it's actually only partially represented. So, okay. I don't know how deep I have to go into that. Is there any questions so far?
Not yet.
Not yet. Okay. Either it's because everything is clear or because everything is very confusing. All right, or both.
Yeah, I mean, no, of course, each of these inference rules is its own story with its own logic and its own truth value formulas. And as you know from experience, to understand that an inference like this for you or me can require like an hour of study and thinking through what all the pieces are. So yeah, I guess someone seeing it for the first time is not going to understand exactly what the AI is doing with each of these steps, which
Right.
is kind of unavoidable, but it's an interesting combination of fuzzy logic, probabilistic logic, some information theories such as with the attraction, and then crisp logical inference, all working together. So there's really a lot that is packed in here. So someone has asked whether we're using embeddings. So we're not using embeddings here at all for this example. So this is a relatively simple example where actually we're taking some results that came out of machine learning analysis for a data set, like this gene is connected with this phenotype because it was important in the machine learning models for predicting the phenotype based on some data set. So I mean, we took data regarding nonagenarians, like people living 90 years or older, and we had their gene expression, and then we had gene expression of match controls who were younger. And so ask Moses machine learning algorithm, which is also part of OpenCog, using genetic programming sort of algorithms to figure out like what patterns would predict whether someone's going to live 90 years or over based on their gene expression. From that, you can see like which genes are critical in the machine learning models for predicting if someone's going to live a long time. But that's not explainable, and it doesn't tell you what the mechanisms are. So then what you can do, you can take all the knowledge in the bioatom space and you can ask, like, can the reasoning engine come up with an explanation for why this gene may occur in all these machine learning models predicting longevity? And then the reasoning engine indeed can come up with some interesting logical explanations for why that gene might imply longevity. So it's just one piece of the picture. Like the other piece of the picture would be using the knowledge in the bioatom space to actually guide the machine learning process, which would be done, for example, if you did the embeddings that Manhin and Debbie were describing, and use the embedding vectors as input to the machine learning algorithm rather than the raw data, then you'd be learning what's in the atom space and be using what's in the atom space to guide the machine learning process, which is also interesting. What Nil is describing is the other side of it, where the machine learning spat something out and you're using reasoning to interpret the result, right? So with a cognitive synergy, you need all of these things. You need the embeddings, so the atom space can produce inputs for a machine learning algorithm doing biodata classification. Then once the biodata machine learning has been done, you need reasoning in the atom space to interpret the results. We need all these working together. What we're hearing here in two successive talks is sort of the two halves separately, and putting them together is stuff we're now actually working on, but don't have a nice slide deck for. So the thing is, these inferences are still kind of slow right now. Like PLN can figure out anything if you give it the data, but it may take a long time. And it's gone from like days to hours to minutes in the time that Noel and I have been working on it, but it's still too slow. So then another use of the embedding vectors will be to help speed up the logical inference by pointing the logic engine in the right direction, not quite literally, where we mean the direction being the vector between the vector for the premises and the vector for the conclusion in the embedding space.
Yeah, and actually, I mean, what Manin has been well, pretty much showing is that we might just be able to use intentional relationships. I mean, if the correlation is that good, I mean, I guess it's not going to be that good in general, but it basically shows an intuition that we had for a long time, which is that, well, intentional relationship is a way to allocate attention if you don't know any better.
Yeah, so intentional logic is logic of properties, right? So for example, a whale is not extensionally a fish, but a whale has a similar intention to that of a fish because it has many of the same properties as a fish. So if two genes are different genes, they have different base pairs, different sequences of amino acids, but the same genes are involved in many of the same biological processes, then those genes would have an intentional similarity, right? And so what Manhim was showing was the intentional similarity between two genes or two categories of genes is correlated with the similarity between the embedding vectors you get from the genes by the deep walk method. Now, to guide biology lab research, we need extensional inference. I mean, we need to know what gene it actually is and what amino acids you want to tweak with CRISPR and so forth to affect a gene therapy. So you do need the precise extensional logic in order to guide, medical interventions to help prolong life in this case, or cure COVID or something. But the intentional reasoning about properties is very, very useful for guiding the extensional reason. And then the embedding vectors are morphic to the intentional reasoning in the atom space. So you have a sort of approximate morphism between extensional and intentional relationships in atom space, and approximate morphism between the intentional relationships in atom space and the embedding vectors. And these approximate mappings are useful for guiding the reasoning processes. And there's a lot of math under the hood here that helps us work out. Like when you're looking at intentional relations in atom space, the degree to which a certain property is part of the intention of a node, like a gene or a category of genes, is how much information does that property give about that node, right? So there's some information theory behind the scenes, as well as some probabilistic and fuzzy logic in the truth value rules underlying each of these logical inference rules that Neil has shown.
Yeah, and yeah, you were mentioning that inference can be used to find an explanation. It actually goes beyond that. I mean, it can be used to just discover knowledge that are just too difficult to be captured by the machine.
Yeah, that's
learning,
what's really cool, right? I mean, in
yeah.
this particular example, the idea that this gene is associated with longevity came out of applying a machine learning algorithm, Moses, to a data set, and we're looking to generate an explanation. But you can also use backward chaining inference with a variable in the query and say, like, okay, which combination of genes, if I twonk them with CRISPR, might cause an increase in lifespan according to all the data fed into the bioatom space from background ontologies and from experimental data sets. And then in that case, you're asking PLN to just make a hypothesis, like maybe if you twonk this and this gene using CRISPR, you can make someone live past 90 when they wouldn't have. Then PLN can come up with that hypothesis and an explanation of why it came up with that hypothesis,
Yeah.
which then guides lab work that human biologists wouldn't have been able to figure out how to do anymore. And that involves the same logic that we're looking at in this example, which is more oriented toward explanatory modeling of machine learning results.
Okay, so like, do you want me to say a few things about the inference itself, or
Yeah, please do.
should I
Please
just
do.
All right, so okay, where do I begin? I'm going to begin with something simple. So here, for instance, we've got that some gene is the member of some Go category. Well, we can infer that if that's the case, the singleton of that gene is a subset of this Go category. Okay, simple enough. Now we can do that over many Go categories. Okay, that's not here. Okay, let me just say a few words about the attraction link. So to get the attraction link, I mean, it's kind of a tricky thing, but basically you look at the subset of some concept with another concept and the subset of the negation of this concept with this other concept. And the reason you do that is because the notion of attraction is basically something, some concept that is usually a fairly specialized concept like a gene is attracted to something more abstract, and you want to find the abstraction that is going to be able to represent well these more specialized concept. And so that's why you look at you look at these things, and basically this allows you to establish this relationship. And if you do that with enough concepts for some gene and, well, many categories, and some other gene, which is here just symbolized by H, and many other categories, then you can establish the intentional similarity. And when you do that, basically what you're saying is that these two concepts are similar by their properties. They might have no member in common, but they might have many properties in common. And once you're there, and then you can just use a regular deduction, but in the domain of concepts, I would say of patterns, of abstractions, to infer that another concept where you don't have knowledge about whether it has this abstraction or not, well, then you can infer the probability that it would indeed have such an abstraction. So that's what it's done here. Basically, we have some gene. Yeah, so we have some gene, and we wonder whether it is it has the property of leading to aging when its expression increases. Sorry. And what do we have what knowledge do we have? We know that this gene has this property, and we know that they are intentionally similar. And so we infer with some, well, probably it might be a low probability, but it's still higher than average, that indeed this gene might have the effect of being associating with aging when its expression increases. Okay, so that's for an example. Well, that's it for the meat of my talk. I mean, the rest is basically a conclusion. Oh, well, maybe I should ask if there's any question about this. I mean, I see I'm already beyond the schedule, but.
So there is a question. It's asking whether you find generalized rules and keep these rules as separate algorithm, or are these rules incorporated in the atom space with new edges and nodes?
Absolutely, they are incorporated in the atom space. So really, what we're trying to do is incorporate as much as possible in the atom space. I mean, it goes even, we're even trying to reformulate the learning algorithms as nodes and links for obvious reasons, self-rewriting and stuff like that, analysis, introspection, and so on. So yeah, question is yes, answer is yes.
And I have a question myself regarding, could you go over the attraction link a little bit more again?
Right.
I mean, you did discuss it, but I'm.
Yeah, okay, here you can see, so what the attraction link is doing is look at the difference between the probability of this, so the subset of some concept and some property, and the probability of this. So the negation of this concept and this property. And the idea is to avoid concepts that would be so abstract that they basically have no longer any discriminative power. So for instance, if you take as a concept here, the universe, or something that exists, it would be, well, it would be true for anything. And so any value here would be 1, and it would be 1 here as well, because the negation, well, something exists and the negation of this thing exists as well. I mean, we're talking about an abstract universe where, I mean, the universe of all things, basically. And then you just have no way to tell that this property universe is just not very interesting. So to tell that it's not very interesting, you consider the difference. I mean, that it's as simple as that. And I mean, currently the difference is used. I suspect it could be otherwise. What is annoying about the difference is that it no longer has a probability interpretation. Maybe we can do something else. Maybe, I'm not sure exactly what. But nevertheless, the difference does capture this idea of that we want the property to have some discriminative power.
Okay.
So it does work for our purpose.
I'm not seeing any other questions. We should have a panel session next.
All right.
To discuss all of these issues. Who's all? I don't have a list of everyone who's on the panel. Is it the people who've talked already? Ben, Mike.
A list of everyone who's on the panel may not exist, actually. So yeah.
Right. I'm thinking it's probably you, Mike, Debbie, Monhin looks like he's still here if he wants to join, and Nil. Is that
That's certainly certainly a good start. We could invite Alexei to join, perhaps. I see he's on Zoom and has been doing bio AI stuff as well, although didn't give a talk in this session.
right? Who else is here on the bio side? Sure.
So that just requires that everyone who is participating in the panel to turn their video and microphone on, and everyone who's not to turn it off, right? So
Yeah, so we can see who's on and
so.
So I guess the question is putting everything together, right? And so we're working in a number of different directions. Ben, perhaps you'd like to start off and put the context into how to combine. So we've talked a lot about bio atom space,
so
embeddings. We've talked about the cognitive synergy, how reasoning fits into that. That's what Nil just finished up on.
Yeah. I'm happy to, Matt. So I've been working on application of machine learning and machine reasoning in various forms in the biology domain since, I guess, 2001, which was shortly after Human Genome Project concluded. That's when it first became clear, like, the transition of biology into an information science was really underway, and we were just going to have way more biological data than you could handle either just by human analysis or by standard biostatistics methods. And what was clear to me then, when I started in this domain in 2001 too, was what you needed to do was take all available biological knowledge, like every ontology out there, all the data from research papers and the graphs and charts and the summaries of conclusions in research papers, ideally the knowledge from biology and chemistry and medical textbooks, and the raw data from experiments on humans and different organisms. And you wanted to feed all this data and feed it into a giant AI knowledge graph, and then do, cross-experiment, cross-organism, cross-level of the organism data analysis. And it seemed like, at that time, actually, people were already connecting simple AIs to robot lab equipment also for microbiology experiments. So, it seemed like the rational thing for humanity to do would be aggregate all data about biological functioning into a giant knowledge graph, and let multiple AI algorithms cooperate on looking for patterns into data and generating hypotheses about how different systems were working and how you could remedy different problems. And this ties in with the discipline of biology called systems biology, as well as bioinformatics, where in systems biology you're looking at modeling and understanding the overall biological organism, from the quantum chemistry all the way up to the social and environmental context of the macroscopic organism and the cultures that it's embodied in. And from a big picture view, it is absolutely insane that the human species is not doing this as a large priority. Like, we're all going to get old and die if we don't do something about it. And on the way there, we're going to get sick of due to various causes, of which COVID is currently the most high profile one. And clearly, the best way to address this scientifically would be by massive scale data integration and then sort of cognitive synergetic AI cooperation on this integrated data. But yet, that's not what's happening in the world today, right? What's happening is biomedical data is siloed off in the databases of pharmaceutical companies, and most of it's proprietary. And most data that's gathered is analyzed in a very simplistic way using statistical tools that, for example, on a large genomics data set with hundreds of thousands of SNPs or tens of thousands of genes, so much work is just statistical methods to try to find one gene or one protein, which is significant, and then do experiments on that rather than looking at the complex combinations of biological actors and the complex networks on multiple scales that we know are what fundamentally underlies most diseases, right? So, I mean, that's the big picture. And now, it's almost 20 years after I started playing with machine learning algorithms applied to genomics data. 20 years later, we still don't have this holistic systems biology knowledge base of all biological knowledge. We are, however, able to come closer than we were before. So we have a nice bioatom space with data from multiple data sets and ontologies integrated. And at least now we're using, we're neural nets, vector embedding, machine reasoning, pattern mining. We are using these things on integrated biological knowledge. So some progress is being made bit by bit. But I mean, I think if we're going to cure aging before I, for example, get old and die, which I would rather avoid, and if we're going to be able to much more rapidly create therapies and vaccines for the next pandemic that hits in 3 or 5 years, whatever, after COVID is gone. I mean, we got to get our shit together as a species and use the best informatics and AI tools that we have to actually aggregate together and study the biological data that we are gathering with our amazing instrumentation, right? And so we're making real steps there. But I think probably the next big step has got to be, we have to make some major discovery in biomedicine by using integrated AI on a sort of systems biology inspired graph knowledge base. And then I think then a bunch of dominoes will fall, and the world will realize that, this is integrated AI and systems biology is just a much more fundamentally solid approach to medicine and biology than the approach that's standardly being taken. But the challenges are significant to make this happen just due to the way the medical industry is structured. So as one example, we've been playing a bunch in SingularityNET's AI group with putting OpenCog together with deep neural nets and evolutionary learning for clinical trial analytics, right? So we're working with a group that's doing clinical trials of multiple antivirals against COVID-19. And so we wanted to get some practice by deploying our AI on clinical trial data regarding a bunch of people from whom you had genetic data gathered and where they tried different therapeutics for different diseases, where you could then use your AI to help figure out like which therapy will work for which person best based on their DNA. So personalized medicine. And I've done work like this before, but it was in consulting contracts for pharmaceutical companies. So it's their data. We can't use their data like now for a public project. So how many open data sets are there that you could use for genomics powered personalized medicine? Well, we found some nice cancer tumor data sets, no open infectious disease data sets, no open neurodegenerative disease data sets that are anonymized and you can just download and use to experiment with your machine learning and reasoning algorithms for machine learning driven personalized medicine. There's data sets that are in principle open, but you need to fill out a lot of forms and wait for some committee to approve you, but those committees aren't meeting due to COVID, right? So, I mean, we're still in a ridiculous situation in terms of just unnecessary impediments to progress, but miraculously, we are still making some progress. And as Matt said, we're now able to pull together probabilistic reasoning, graph pattern mining, neural net embedding, machine learning using neural nets and XGBoost and other decision forest type methods and standard bioinformatics tools from RStudio and so forth. And we're able to pull these together to actually do some hypothesis generation and so forth. And I think in a way, this work is even harder to aggregate people toward than AGI work, because we're doing machine learning, we're doing proto-AGI work in quite complex software systems, and we're doing biology. So you need to actually understand something of the biology and chemistry and systems biology as well as machine learning and proto-AGI data structure. So it's not something that many people are well prepared to do yet. I think it's the only way we're gonna cure aging and be able to more rapidly cure diseases. So yeah, I think we've got, on this call, a bunch of the people who have been in this panel, a bunch of people who have been sort of helping me push this work forward in practice. And I think everyone has brought to it their own copious experience. And I think, Debbie, it might be interesting for you to say a few words just on how you look at systems biology and integrated AI as being important toward understanding the complex systems involved in biomedicine. I mean, you've worked on this from a sort of health insurance data analytics standpoint and from a whole bunch of different angles.
Yes, okay. I've also been in integrative AI for a long time, maybe from the 90s, but my angle was computational social science. So I've looked, and my work has been based on ideas from hermeneutics and basically autonomy. Brooks and Steele's, had also the idea of autonomy, but autonomy is very important in my work. I wrote the symbolic interactionist simulation of trait and emergent roles, where agents are really reinforcement learning agents, but what they learn is a kind of interface with each other that places each other within a role, and that's based on sociological micro phenomena like symbolic interactionism. So as agents interact with each other and transact with each other, they learn what each other can do and develop this language of what they can do. And this is basically the kind of thing that you're doing, except I emphasize, and I don't know that you're not, but I emphasize diversity and autonomy. Like, these agents are really separated from each other, and to connect to each other, they have to develop a common language. And I don't have one agent looking inside the guts of another agent to help it with its guts, right? Which is kind of like what I think of, and maybe I'm wrong, the cognitive synergy idea. But rather, I kind of force them to, if they're going to cooperate together and maybe, for example, in a market, make a product together, they're going to have to find out what each other can do, develop a culture of what each other can do, and have that continue and become like a common expected interpretation of the signs that each other are presenting to each other. In an emergent, system that develops between the agents, right? And so applied to biology, well, since he's a reinforcement learning agent, you have a goal, and your goal is to maybe make a product, right? But all these agents are involved in making different software projects, right? And as they develop, supposedly, as they have experience in making these different products, they come to have roles that can be transferable between products. So the interface between them comes to represent more detailed requirements. right? And those requirements come to be general. So it's really a distributed market program, which takes advantage of market processes so that in the development of agents, so that price becomes a way of distributing credit and or assigning credit, so that agents know what credit they're assigned and what and their interface, the sign that they display to each other of their role comes to mean a detailed requirement list that's general, that can be reapplied. Now, most multi-agent reinforcement learning systems don't have this ability. Even though they have the transferability, they don't have the ability to transfer individual roles across systems. And so they don't have that generalization of the role and the abstractness that comes with it. So, I bring these ideas to complex systems, and it's a little bit different, but have many things in common with the OpenCog paradigm. And in particular, we can take different neural methods and different transfer learning methods and have those embeddings, signed to each other about what has been included in them, and that's useful for particular projects, so that those things can be reconfigured. So the reification of symbolic interactionist paradigm makes it so that we can reconfigure roles into systems that apply to each different kind of problem. Any questions?
So what Debbie is describing is AI framework, learning and computational creativity and data analysis framework called Sister, which she's written about, which you could find out by looking in Dr. Deborah Duong Sister online. There's publications on it. It's very cool, and it is not integrated with OpenCog at this moment, but I think sort of similar to the cogistry algorithmic chemistry approach to computational creativity that I briefly allude to in my introductory talk. Sister is another very interesting algorithm for sort of collective self-organizing swarm-based learning, which I would like to be able to implement a scalable, huge-scale version of distributed decentralized sister algorithm on top of OpenCog Hyperon, next generation OpenCog system. I mean, just like the cogistry system, because I think this gets back to the notion of sort of explicit knowledge representation and explicit reasoning versus emergent creative learning and the emergence of new representations, right? So when we look at a gene node and a protein node, a molecule node, a node for a specific patient, a node for longevity, and we do logical reasoning on the inheritance, implication, attraction links involving these nodes. I mean, this is important, and it's one level of reasoning that has to be there. I mean, it's explicit logical inference, and this is science. It's molecular biology, which is a formal system. So I mean, this explicit inference is important there. On the other hand, a system like cogistry or like Sister that Debbie just outlined, this is a self-organizing system of agents that are all cooperating and transforming each other and collaborating with each other. And you then have emergent knowledge coming out of the organization of all of these agents. And this is also important. And it can connect, because if you had cogistry or Sister operating on the atom space, I mean, the emergent knowledge that's created there as related to a gene, for example, becomes part of the property set associated with that gene, which is part of the intention of that gene, which is then used in reasoning and in creating embeddings, right? So it's a few steps beyond where we are now, although we're working with all these systems now in simpler ways. But ultimately, what we need is these sort of self-organizing, fundamental emergent knowledge generating systems running on the knowledge bases about genes and proteins and biological data, and creating new patterns that are then used as properties inside explicit logical reasoning. And you also, of course, need the agents inside a sister type system like Debbie described. You need those agents to be doing reasoning, using Nill's reasoning system to foster their interactions. So there's a lot more threads here than one can go into in merely a few hours of discussion, right? But hopefully we are at least giving pointers that people can follow up with for further discussions. No, one thing that we've been working on before, which wasn't specifically bio-related, but certainly plunges in here, was automatic learning of inference macros, like combinations of inference steps that are going to be reused a lot, as well as automated learning of inference control strategies, which I think are going to be important in the bio-AI domain as in other domains because of the complexity of the inferences involved. I don't know if you have anything pertinent to say about that, no?
Yeah, so I didn't get the chance to experiment with inference control learning on the bioatom space, but it's very clear that it's going to be needed. And what we're going to need as well is we're going to have to incorporate attention allocation, because the problem I'm having now is that basically a single rule application can be extremely costly if it considers the entire atom space. I mean, when I say extremely costly, I mean, it can take like dozens of minutes. It can completely explode the RAM of the machine. And this could be simply avoided if we just integrate ECAN, which stands for Economic Attention Network, and just select the atoms that are supposed to be the most relevant. So I think that would definitely be the next item on the list. And then once we have ECAN integrated, then we can start to play with inference control learning. And I suspect that we can do a lot with ECAN if we incorporate as well contextual Hebbian links, which I don't think we had a chance to play with that yet.
Yeah, so I think that's right. So there's a bunch of stuff we'd experimented with in other contexts that we haven't yet ported over to the biology case. So I mean, ECAN, economic attention networks, is spreading attention among different nodes and links in the atom space, and that can guide the logic engine in knowing which nodes or links to pay attention to at each point in time. And then pattern mining, what we were doing was saving a huge atom space of all the inferences that were done in the primary atom space. So you have like the bioatom space with all this knowledge in it. You're doing reasoning there, but then all the steps of reasoning that are done were stored in this auxiliary inference history atom space. Then you apply OpenCog Pattern Miner to look for patterns in the inference history atom space, and you can find patterns. And well, doing this inference step followed by this inference step, doing it like a deduction followed by Bayes rule followed by attraction rule. You know, when you're looking at inferring similarity between two genes is highly productive, whereas doing 4 deductions in a row when you're looking at similarity between two genes is not productive, right? So you can learn patterns regarding which combinations of inference rules tend to be useful in which contexts. Then once you've found those patterns via pattern mining and reasoning on the inference history atom space, you can deploy those patterns to help pair through all the possible series of inference steps that the logic engine is doing. So you have ECAN, the neural net-like activation spreading to guide to help choose which premises to use in inference. You have pattern mining on the history of saved inferences to help guide the choice of which inference rules to use. And then you have what Manhin talked about, which is using directional arrows in the embedding space between premises and conclusions to help the inference engine choose intermediate goals along the vector in the embedding space. So putting all these tricks together, the idea is to solve the combinatorial explosion problem that has plagued logic-based AI since the beginning, right? Because it's always been clear logic is an incredibly powerful approach, and you can apply it without, hand-coded common sense knowledge, as was done in the original logic-based AI in the 60s, 70s, and 80s. On the other hand, you have to solve the problem that there's just too many possible inferences. You have to be able to prune the inference space, and I've just described 3 ways you can use cognitive synergy to prune the space of logical inferences, and we have sort of prototype explorations of each of these ways to prune the logical inferences. The bioatom space gives a highly important as well as very concrete and practical playground for experimenting with these different ways of pruning uncertain logical inferences. But that's sort of among the work that is in the next step for us, is to experiment with all these methods, individually and in combination for controlling and pruning inference, so we can do more and more complex inferences in a way that doesn't take so long. And then, of course, scalability on the knowledge graph side is the other side of things, because we're already at the point where we have to pick and choose what goes in the bioatom space knowledge graph so it will fit into RAM, and so that the AI processes, as they're now implemented, won't take forever in running on it. And we need a bioatom space that's spanning RAM on many machines, and we need the cognitive processes to be written to more effectively exploit distributed processing and concurrent processing, because it's what we're doing now. It's already fairly big data, but to really solve biology, we need huge data. Going back to what Mike was talking about in the first talk in this panel. Mike, if you're still on here, do you have any comments to add based on the AI that has been dug into in the couple hours since your talk?
You're muted. Mike, you're muted.
Mike, your
sorry,
your mic is off.
I'm so sorry, Mike. I wanted to unmute you, but then I muted you because you were first.
Okay, no problem. Can you ask a more specific question?
I have a question.
Well,
Okay.
I think a more specific question would be, what sorts of inferences do you think will be made possible once we've more fully solved the inference control problem? One interesting thing to talk about this way is we would talked a while before about stem cell differentiation and transdifferentiation, and what we could do there with Moses and PLM once we'd solve these scalability problems. Just as one example of a bit more advanced bio AI reasoning that we're working toward.
Well, I guess I've been thinking about more like a shorter term project of doing. Well, one of the problems with the bio research that does exist is that it's concentrated on just the sort of sociology of the science, concentrates research on a narrow subset of the known genes. So like in the gene ontology, we know a lot about maybe like 10 to 20% of the known human genes, and the rest of them are just sort of less well known. We have sort of like more experimental, information on large scale, screening experiments about what these proteins, how they might interact with other proteins in a petri dish, but not in in living organisms, let alone in people. So we could sort of like think of that as like a graph completion problem. So we've got like examples of some genes that we know a lot about and a bunch of genes that we know a little about. And so can we sort of like make analogies about what we do know about the sort of unknown genes? I mean, we know their amino acid sequence. Maybe we know some locations for them. We know how they might interact with other genes, even if we don't know, what they're actually doing in living systems. And then from that, you could just make sort of like hypotheses about all the possible potential biological pathways that could exist. And then, and that's a huge number, but it's still finite. And then, so we'd have all this, so those are all just hypotheses about how, so then we have some experiment where we've got a gene that we don't know much about that comes up as being, say in a GWAS experiment or an expression, a transcriptome experiment where this one gene is expressed a lot in a disease state and not in a normal state. And then now we have all these potential, theoretical pathways of where that might involve this unknown gene. And then, other genes that are in the habit level pathway, maybe we can connect them to stuff that we do know and sort of arrive, and that, I mean, there's enough information where you could make hypotheses about what's actually going on and, in completing the, these missing parts of the knowledge graph. And then there's an experiment that could actually be tested. So
yeah, very interesting. I think that ties in with stuff we've discussed regarding automated pathway discovery, right? Which is closely related. I mean, the definition of a biological pathway I like to use is it's a subgraph of a biological network that fits on a single journal page, right? And I mean, it's a little bit tongue in cheek, but I mean, there's a certain set of biological networks that are well understood and well studied and are called biological pathways. But then, there's a huge amount of network interactions in humans and other biological systems that are clearly there and are significant, but no one's drawn a picture of them on the journal page, and they're not well understood. And you could use the biome space right now to discover novel biological pathways that are implicit in the protein-protein interaction and metabolomic, genomic, proteomic data that's out there. And then you're getting into hypothesis discovery again. And this gets into something that I was thinking about a lot when I was working with Genetian. So at Genetian, we had these long-lived flies that live 5 times as long as normal flies. And you could do a lot of machine learning work to see, and biostatistics work to see, why do these flies live so much longer than normal flies? Because they were created by experimental evolution, by crossbreeding over 40 plus years, not by genetic engineering. But when you're mapping fly genomics into human genomics, I mean, there's orthologies between individual genes, but that only gets you so far. And often you see some process in the fly, say regarding the fly's neural processing and neurodegeneration, some process is analogous to a process in the human brain, but the analogy isn't just mappable by orthologous genes, right? So then you're looking at, can we use abductive reasoning? Can we use analogy reasoning to map a process or a pathway in a fly to an analogous process or pathway in a human? And sometimes that's using, pathways that haven't been explicitly identified as pathways in the literature yet either, because Drosophila pathways are studied a lot, but not quite as well as human ones. So that's a case where you want, abductive PLN reasoning directed by graph embeddings. And, the payoff could be large because we know a lot about how to extend flies' lives, but there's similarities and differences to humans, because a lot of things you do to prolong life in a fly will cause cancer in a mouse or a human. So you need to figure out not only how to map what prolonged life in a fly into a human, but how to map it in a way that will dodge the differences between flies and humans, including things that are carcinogenic in humans, right? So these are subtle AI problems, yet we have massive amounts of data that could be used to fuel this type of reasoning.
So I had a question for Mike.
Sure.
I'm not my biologist by training at all. And I was fascinated by that video that you shared and watching everything happen. You know, the splitting of the cell, dividing of the cell, or the DNA moving around. And I think it comes down to kind of what Debbie was working on. What's governing all of what's going on there? Is it the actual genetics, the epigenetics, or is it an emergent phenomenon a la sister? Perhaps?
It's definitely an emergent system. And I think that's one of the big parts where there's just really isn't much known. I mean, it's a very hard thing to experiment with, but we do know we know a lot of the parts, and we know sort of, how cascades, signaling cascades where, one gene, one protein function is to turn on a bunch of other proteins in a certain context, and that guides, cell development. So one cell turns into another when you have an organism turns in from like, a single cell to a complete, multicellular organism. And we know those kinds of processes. And it's just in biology, it's just happening on just like a massive scale with like millions and billions of parts. So, I mean, even now, to the extent that we can scale stuff to our, our processing capacity, we can get, we can start taking all those pieces and just setting up in a big system and seeing what kind of emergent properties will result. I mean, for the bigger, and I think we can get a long way just by like, because I think we do have most of the pieces, and just sort of seeing what, reproducing what we already can see happens in living systems.
So
I do think that the part that's missing, I mean, in terms of our biological knowledge, is going from the chemistry and the biochemistry to sort of like the whatever it is that in the changing level of complexity from like non-living systems to living systems, which is hard to define, but I think it's sort of clearly there in some sense. And my own theory, is more, I think it's going to come out of understanding sort of the larger emergent sort of electromagnetic field structure that comes out of all of these molecules working together, which is, I mean, that's a whole.
Yeah, and I want to add here, like right now, we're using a layered series of abstractions that's been created in the fields of chemistry, biology, medicine, and so forth, and mapping that into OpenCog because that's the tractable thing to do, right? But it would also be very interesting to take the rawest possible data from all the instruments we have and like feed it into deep neural networks to recognize low-level patterns in the data and let the AI build up its own abstractions. And I've thought about this in the physics context also. Like what if you turned AI loose on data from particle accelerators and bubble chambers and so forth, like would it learn a different system of concepts than what we have learned to describe what's happening there? And this could be the case in biology in some cases also. I mean, obviously the concepts that we have are great and are very, very meaningful. On the other hand, when you look at epigenetics and when you look at the processes going on spatially in building up a cell, it might be that there's new concepts and patterns that the AI will discover to help describe the self-organizing processes that are going on. So I mean, in the medium term, you want to feed all the raw data in the AI and see what concepts it can form. Although right now it's hard enough just to grope with the genomics data as conventionally conceived.
Right, and there, I mean, there's definitely work going on along those lines, taking just more raw experimental data in terms of mass screening, where you're seeing which proteins interact with other kinds of proteins, in a test tube, and just the results of different kinds of experiments, and then actually evolving, deducing ontologies from that, and that's been done outside of OpenCog in different ways. But that's, I mean, I think that's a whole line of research is going from the raw material, some of the raw experimental relationships, just as you said, like from, and maybe including sort of like laws of physics, notions of spatial, 3D dimensional spatial relationships and chemistry kind of stuff, and then sort of deduce from that the gene ontology or something gene ontology like. I mean, that's one whole, I think, and then, I mean, and sort of, there's also the aspect of getting, like a lot of these databases, you can look at them as sort of, I mean, if you think of like human, the totality of human researchers as like an intelligent system, sort of synergizing with an artificial intelligence system like OpenCog, then how can we get like the ontologies are sort of like a synthesis of a bunch of like research experiments, and they're right up in biological papers, and then so other people like extract like the gene ontology from all this research. Where was I going with this? But we can also like automate it from, I mean, this is not using bioatom space, but just sort of like the OpenCog research on natural language understanding, where when that's developed enough, you could just sort of start dumping in research literature and evolving ontologies from that as well.
Yeah, so I think I guess there's an interesting question in the chat, which is the proper prior structure for inference control suspected to be domain dependent? And I think Neil will have a view on that. I mean, I think it's partly domain dependent and partly not domain dependent. But I think one thing we found when looking into automatic learning of inference control heuristics is, so there's some things that clearly are just general purpose, like you don't want the inference engine to try to build up huge amount of nested universal and existential quantifiers unless it really has to. Like let it try to find simpler things first, and probably like reasoning A implies B, B implies A imply B, B imply A over and over, repeatedly reversing things with Bayes' rule is dumb, right? So I mean, there's going to be some general inference control heuristics, but it seems like once you get a little deeper, it does get domain specific and very specific, like the series of inference steps and premise types you want to use to reason about what groups a person might belong to, or reason about what pathways a gene might belong to. There may be kind of specific inference control heuristics for these very special kinds of inference, like gene to pathway or person to social group. And this is what drives you to realize, well, you need automated learning of inference control heuristics, because there's going to be heuristics at multiple levels of generality. No, I don't know if you have anything to add to that from your experience.
Yeah, so from my experience is that domain dependent controls are just going to be.
You're very quiet now.
Yeah. So domain-dependent inference control rule are just going to be easier to learn or to infer. And then, I mean, except for, you know, the obvious example you gave with the, you don't want to do inversion and go in a pathological loop. When you go past these sort of things, the more general the inference control rule is going to be, the harder it's going to be to extract. And it's going to have obviously more value because it's going to be more general. And the question I'm really wondering is, could it be as general as to be applied to the reasoning that is involved in finding inference control rules? And if that's the case, then as you are just improving the system to be more efficient as reasoning about real world problem, you might just end up also improving the system about reasoning about its own improvements.
Well, now we're getting to the heart of the matter of superhuman AGI, no, right? Like, I mean, if the automated learning algorithm can learn the particular inference control heuristics that are appropriate for meta reasoning for the learning of inference control heuristics, right? That in a way is a little bit specialized, but that's specialization to self-improving learning of inference, right? And then once you're there, I mean, then we've done what Jürgen Schmidhuber said is his career goal: build an optimal scientist and then retire, right? So I think yeah, that's a very interesting question of you know, what are the inference control heuristics that are particularly useful for the problem of learning inference control heuristics. And clearly that's a couple steps in the future, because we're still at what are the inference control heuristics useful for learning when a particular gene is relevant to a certain pathway or something. But it's the same formal structure of problem, right? And I mean, we now have the tooling to address that problem, but clearly we need to address some infrastructure scalability issues before we can pragmatically address the problem of learning the inference control heuristics that are optimal for learning inference control heuristics, which again leads on to tomorrow's discussion on the improving infrastructure scalability and so on. And I think we may have used up the time for this panel now, although Matt, if there's something else.
Well, I was going to say your comment serves as a perfect segue into the precursor, basically, I guess, from the title of Linus's keynote on thinking about the atom space, knowledge representation with graphs. So maybe that just serves as the transition.
Yeah, absolutely. So we're segueing away from biology back to the core of OpenCog, and the next speaker, Linus Vepstas, is going to give an in-depth keynote talk about the OpenCog atom space, which he is uniquely qualified to tell us about, since Linus has been the lead software developer and theoretical mastermind behind the OpenCog atom space, as well as many other aspects of OpenCog, you know, for the last 12 years or something. I mean, if you look in GitHub at OpenCog, it's very hard to find a piece of it that hasn't had a significant contribution from Linus, both code-wise and conceptually. So I mean, we're incredibly fortunate to have had his intensive contribution for all these years, and he's going to give a bit of his view on some aspects of the atom space, sort of a meta representational framework that he's played a key role in developing and shaping over the years. So yeah, let's turn the microphone over to
Linus.
Dr. Linus Vepstis, coming to us from Austin, Texas.
Hello, everyone.
We hear you. We see you.
Welcome.
Good. All right. I'm going to, well, let's see if I can figure out how to do screen sharing here.
Down at the bottom.
I clicked on it. Oh, there we go. Desktop 2.
I also just shared your slides with the community. So if they want to follow along, the slides are shared with them in the chats.
Yeah, I put some work into this to try to make it work right. Anybody want to take any bio breaks at all? 3 minutes before I continue, before I start up here?
I think we're good. There are
Yes,
about
yeah, we're all robots here. It's all right.
All right. With today, I want to focus on, I guess I'll say the nuts and bolts, very sort of low-level stuff in comparison to what has been talked about so far. It's about the atom space. You may or may not have encountered before as a graphical database. And some of the newer features, things you can do with it. I'll try to squeeze in 3 different topics. Something called the Matrix API, which has been present there for a while. It's underutilized a bit. I'll talk about values and value flows as a generalization of truth values. Everyone, all of the users of OpenCog are familiar with truth values. This sort of pushes them a little bit farther off. And then I always save the best for last, my favorite topic. Connectors, I'm calling them connectors and bonds these days. And there's a little picture of like a cloud with 2 antennas sticking out. That will be what this whole talk is about, these 2 little connectors sticking out of a cloud of relationships. All right, the matrix problem, the matrix API. So there's a generic problem in data science that you often have correlation matrices of stuff, matrices of numbers, and what in Facebook and Google, I think it's customers and their product preferences, right? You have 100 million people using, Facebook has what, 6 billion people on it, and they all have ideas about their product preferences for 10 million different products that vendors are trying to sell them. You have this huge matrix, what people think, what they want. For most of these people, you have absolutely no idea what they want. So it's a very sparse matrix. It's mostly all zeros. And so what I'm trying to write here is, here's a matrix, here's, well, the 2 indices. It could be a person, a product preference. It could be a probability, co-occurrence probability of X and Y occurring together, conditional probability. And here's my little bubble, my little graphical representation with 2 antennae sticking out. Right. And here I'm just using generically I, J, X, A, B. All of these things can be the different parts of your data. I've been working with linguistics with words, but we've been hearing a lot about genes and proteins and genomics today. The point is these matrices are extremely sparse, right? The English language has, the full English language has something like 100,000 words. So if you imagine all word pairs, all possible word pairs, there are 100 billion of them. But only, there's only what, maybe 10 million, maybe 100 million of them actually make sense. Genetics, same way, right? You have a gazillion genes, but only, pairwise interactions between the genes are just a tiny, tiny fraction of them, 0.00001% of them interact. So the trick is, how do you represent this data? And, well, symbolic relational AI is the classic way of doing that. In OpenCog, we You should be able to recognize this. We've been representing knowledge essentially as relationships. Here's a generic one, right? Two genes, FLNC, who knows what they are. One of them upregulates the other. We indicate that. Here's a predicate. We say it's true when the first gene upregulates the second gene. You can have all sorts of different notations. So to connect to the last screen, here's my matrix with matrix entries. Oh, it's a probability of co-occurrence, or I could write it as a relationship. It is true that something upregulates something else. Where did the numbers go? This is the values. So we solved this problem, and I guess I'll call it classic OpenCog, classic atom space, is saying there is a key value store for each and every atom, right? I have an atom. This evaluation link is an example of an atom, right? I can attach to it any value that I want, and to be able to find that value, I'm going to specify some key where it is located at. But the predicate was also an atom. The list here is also an atom. The gene is also an atom. So in fact, I can stick these, I can put this key value database on any kind of graph at all. This evaluation link was a very simple graph, right? It was, here's my two antennae sticking out, and here's some cloud. I'm just attaching values to those clouds. I'll come back to key values in a moment. I'm going to wander off topic. I'm going to stick to matrices for a little while here. There's a subsystem that's been around for a while, but it's heavily underutilized. Currently, it only has a scheme API. I know many programmers don't really like to use schemes, so I'm going to ask for Python or R bindings for it at the end. But let me walk through what is possible today, right? So module is just called matrix. It provides an object-oriented API to any graph in the atom space. The technique for providing this is, if you look it up on Wikipedia, it's called parametric polymorphism. And it's straightforward. You say, okay, I'm going to specify, I don't know, a genomics object. On the left-hand side of that matrix, I'm going to have genes. On the right-hand side of that matrix, I'm going to have genes. Oh, here's where the values are going to be located at. They're going to be located at this thing called an evaluation link. Oh, how do I get a number out of that? Oh, well, I'm going to declare it given a pair of genes. I'm going to say, oh, my number is stored at some key. And that number could be, I don't know, the rate of interaction of those genes, how strongly they up-down regulate one another, how frequently they are found in some bacterium, how, you name it. Stick some number on that key. This is how you can get access to that number, right? And all I've done here was to define a matrix object. That's all that this really is. It just says left-hand side is this, right-hand side is this. Here's where the stuff is. But otherwise, it's a graph, some bubble, some antenna with things on it. And once I have a matrix, I can do all the standard matrix types of things, right? I can ask for frequencies. I can ask for marginal probabilities, right? What's a marginal probability, right? So I have a matrix. I have row vectors. I have column vectors. If I have a row vector and every number in the row is a probability, well, I sum up all of those numbers. That's a marginal probability. That's just the sum of all the numbers in that row. Now, again, this is extremely sparse. It's an extremely sparse matrix. So I'm going to have, out of that matrix, out of that vector, 99.99% of those row or column entries are going to be 0. So I'm ignoring them. All right, that's why I wanted to use a graph to represent that knowledge. It's not dense, it's sparse. But under the covers, looks like vectors and matrices. So I can do all the standard things you do with vectors and matrices. I can compute the mutual information between two vectors. Just, look it up on Wikipedia, apply the formula, there it is. I can compute the cosine similarity, right? Called the dot product between two vectors. Actually, the arc cosine of the dot product of two vectors. For neural nets, right? All the standard neural net papers are always talking about dot products of vectors and matrices. That's their standard, part of their standard toolkit. I can get the length of a vector, Manhattan distance, whatnot. There's even some tools in there for filtering data, right? I don't like these columns. I don't like these rows. Throw them out. Throw away all the data where the certainty is less than 5%. Throw away all the data where the preference expression is less than 50%, right? You can cut and slice and dice as you wish. Now, this is all in a scheme toolkit. And I know you guys, right, the guys who are actual data scientists out here, they say, no, 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 I want to use GNU-R, or I want to use SciPy, or I want to use some other toolkit. And so I'm going to, with this call, I say, look, this isn't hard. We can specify a matrix, provide that interface for GNU-R, provide it for SciPy. You can crunch your data all that you want. For R, I actually looked into this. So for R, actually, it's very easy. There's a tutorial you can find on the net that shows exactly how to plug in your own data, your own vectors and matrices into R, and then use all of the standard tools in R to crunch those numbers. SciPy, it's a lot trickier. In Python, I haven't been able to figure out how to actually get Python, how to push a sparse vector into Python. Python just wants to fill out lots and lots of zeros. And obviously, if you have a million zeros, that's not going to work. So for Python, you'll need some work. But it would be nice if we could get this into SciPy as well, because that way people can crunch data as they wish. It's not hard to program this stuff. So the programmers out there, software engineers, here's a great task. What do we got next? All right, well, I'm flying through these charts. So let me return to values. I talked about values. There's a sketch of what they are, just sort of a reminder of where we've gotten to with the atom space with values. There is now underneath it all, there's something called a float value. String of floating point numbers, 1, 2, 3, you name it, whatever numbers you want to jam in there. It's actually always in the form of a vector, simply because that's the easiest and simplest way to make the storage compact, to not use much RAM. It just, you pack those numbers together so you have, you're not just wasting RAM in some way. The old timers will recognize the simple truth value. It's got two numbers. First number is a probability, 99% chance of it being true. Second number is some confidence, right? 60%, I have a 60% chance. I'm confident with 60% on this. It's just an example of a string of numbers. No need to limit myself to numbers. I can have a sequence of ordinary ASCII strings, UTF-8 strings, words, whatever you want in here. I can go hierarchical, right? I can specify, I can mix these up in arbitrary order. So a link value is much, those of you familiar with the atom space, right? A link value is much like a link, except that it holds these mutable values. I've written them in sort of a scheme format, but you could also think of this as JSON, like this link value. You could say, okay, well, that's, if I want to, I can just make that into a JSON structure. Some of these actually support import and export of these things as JSON for those of you who like those sorts of things. But the title of this slide is values are mutable. So one of the generic types of values is something called a stream value. A stream value is meant to be a wrapper for, say, an audio feed or for a video feed or anything that is changing over time. It might be streaming. The prototype example is called a random stream. It's just hooked up to a random number generator. It's just generating numbers between 0 and 1 at whatever rate that you want it to be generated. You can do things with those streams, right? One of the existing streams is something called a Q value, right, which I can call a FIFO or a buffer. I can push stuff into it, it'll remember them, and out the other end, I can pull stuff out of it. It'll hold it in the meanwhile. The default Q value even has a high water mark and low water mark. So if you're above the high water mark, the writer will stall. The writer can't push anything more until it empties out a bit. There's a low water mark. Once you hit that, the writer unstalls and the writer can start dumping stuff into the queue again. Meanwhile, some other thread can read those values as quickly or as slowly as it wishes. You can transform those streams of data, right? There's something called a formula stream I'll show on the next slide, I believe. But okay, some of you have used TensorFlow, right? TensorFlow for deep learning is an example of one of these kinds of things, right? In TensorFlow, your tutorial, your 101 tutorial always says, hook up your data input from here and your data input from there, and we're going to mix these together and dimensionally reduce them to this or to that, and then send that off to the GPU. The GPU will crunch some numbers and push those numbers back to you. That's an example of a stream that is processing, you know, of a value, of a mutable value that's processing some stream of data. It just happens to be doing it on a GPU rather than doing it on the main CPU. And so under here, I should have written another bullet. I should have said TensorFlow stream or TensorFlow value. It's another way of offloading and processing some of the data. But just to keep things concrete here, here's sort of an example of, oh, sorry, that's going to be my next slide. Hold off. Okay, before I get to the next slide, I want to talk about, here's how you move values around between atoms, right? Again, we have atoms, a foo and a bar. They have attached to them some values located at some key or some other key. Well, I can just write more of the same, get the value of this one, set it on that one. This is how I can pipe things around, how I can build connectors from one spot to another spot and move things around. Now, the reason I'm belaboring something so obvious, because this, I mean, you're looking at this and your eyes are glazing over and saying, this is really obvious, right? It's really obvious because it's declarative knowledge, right? In declarative knowledge, right, the textbook example is dog is an animal, dog has a tail. Heard about intentional inheritance and extensional inheritance all morning. And they're declarations that something is true. So when I say dog is an animal, I say, oh, that's a statement which is true, or maybe it's true with some probability. Well, I don't have to talk about dogs and animals. I can talk about I can make any declarative statement in this fashion. And here I'm declaring that there's a concept, there's an atom, attached to it, there's some data. And I'm declaring that I'm going to go get it. Here's how you can go get it. And that it should be attached to some other atom at some other location, and just attach the thing. So it's just more declarative knowledge. It can be stuffed into the atom space. It's not a programming language per se. It's just it's just some more data that you've jammed in there. But that data can be anything. It can be a way of copying here, or it can be arithmetic, it can be formulas. And so when I was blabbering about formulas in TensorFlow, here's maybe an example of a transformer, a a formula that can take some kind of an input and do something with it. The input, well, I gave it a name, I called it a variable, I said it's X. I'm going to add 1 to it here, plus 1 to that variable, and I'm going to multiply it times itself, and then I'm going to divide it by 2, and that's something called a triangle number, right? It's like a square, but it's half the volume of a square, so it's a triangle. I think the ancient Greeks talked about triangle numbers. This is very verbose. It's somewhat typical of the atom space and atomese. What makes it different than C++ or Java or Python or anything else is that this is all entirely declarative. This is something that lives in the database. And since it lives in the database, it's searchable. And one of the things I can do is I can say, find me all of those formulas which use plus, or find me all of those formulas which have the number 2 in it. Or maybe I should say, find me all of those formulas which have division in it, and that division is by the number 2. And that database will go off, the atom space will go off, and it will find those things for you. And you say, aha, here's my table of all of the formulas I have on hand that involve division by 2. Never mind what kind of graph, what kind of gunk I might have in the middle. And so this is, Ben talked about siloing data. This is a way of unsiloing your expressions, of taking programming out of the silo of having a human understand it and turning it into something machine understandable. Okay. This is verbose because this isn't meant for humans. This is meant for other algorithms to look at these formulas, pattern mine them, data mine them, what Nil was doing, create inference chains with these formulas, apply attention allocation to them, get a list of all of the formulas that we have found, and they're all representable in this kind of a way. So again, I'm sort of sorry it sounds simplistic, but simply making it work so that you can have other algorithms find the data, have one algorithm generate data that another algorithm can introspect and understand its internal workings of, is kind of tricky, but we have a way of doing that. All right, this is all leading up to what is in the end my favorite topic. I always save the best for last here. So best for last, here's a cloud. The 2 little antenna, right? This was my matrix with its 2 matrix entries. Well, we're going to generalize that a little bit. But first we're going to be ultra simple, ultra obvious again, right? So feel free to, don't feel free to doze off. This will be obvious. This is stuff you've known all along since you were a child because it's so painfully obvious. I'll show you why it's not obvious at the end, right? But we have this abstraction. It's called a term, right? Some function of X, or maybe it's a function of n different symbols. Standard notation here. Well, what's X? Oh, well, it's some variable. Could be, what could that variable be? Could be some value, 42. It could be a string, or it's if we're just having functions, you could just be passing any kind of an argument that you want to that function. How do we do that? Well, you take the value, you plug it in, right? It's obvious, right? If I have a function that takes numbers and I plug in 42, I will get an output function 42. What am I saying? Call a function with argument of 42. How hard is this? Right? Plug it in, turn the crank. We say plug it in and turn the crank so often we forget what it means. Okay, so diagrammatically, I've drawn, here's 2 things I can plug together. I've drawn them as jigsaw puzzle pieces because they have to match, right? This part was f of x. This part is a number. X can only be a number, and so the jigsaw pieces have to mate together. If I have a function that only accepts numbers, the thing that I'm plugging into it better be a number. It better not be a string or an object or some Java bytecode or whatever. I know I don't accept Java bytecode. I accept only numbers with these two puzzle pieces. But by drawing this, I've erased something fundamental from the last one, right? Which one is the function? Doesn't say. Which one was the argument? Right? Who called who in this picture, right? All I really did was I joined two things together, and I was completely agnostic about who and what went into where. I'm rather focusing on the fact that I'm connecting things together. And I can do this generically. Here I've drawn a function that takes, I don't know, five different variables. It's a fancy mathematical name for that is to say, oh, it's a tensor. It's a tensor that has 1, 2, 3, 4, 5 different connections on it. So 5 different indices. And when I connect them together, which is the whole point of this, right, is that this looks like tensor contraction, right? So here's V, a vector. It has some index, mu. Here's a metric tensor, right? I've contracted these two indices together, which basically is called Einstein notation, right? Summation says, I'm going to take all possible values of mu, and I'm going to just run over this sum. Here's another vector. It's actually a tangent vector. I'm going to look at the entire tangent space and connect up this index to that index and run over all possibilities. So diagrammatically, I just drew that here. Well, obviously, I have a whole bunch of extra connectors on here. But this is a commonplace, well-known operation of contracting together things together. The point here is I contract two things. The connectors, I mean, it's if these are jigsaw puzzle pieces, I still have what looks like a jigsaw puzzle piece with some unconnected connectors with it. And now I want to go back and say, okay, so great, whoop-de-doo. What's the point of this? And we have to go through some examples for that. Okay, so here was my n area, my function with n arguments. How might I represent that in the atom space? Well, for historical purposes, I'm calling them sections. I'm going to give it some name. I'm going to specify the sequence of the arguments that function takes. I'm going to call them, this time I'm calling them explicitly connectors. I'm going to say, well, here's a connector type. It has to be a numeric variable. And I'm going to give it a name, label it. You don't have to label it, but in this example, we're going to label 1 through n. Well, but I said connectors are generic, so here's another one, right? Here's a section. Here's something I'm going to name it. Oh, wait, but what is this? This is linguistics now, right? Subject, verb, object, standard English construction of language. I've got a verb in the middle. I must always have a subject, a noun on the right. I must always, not always, only transitive verbs, have an object on the right-hand side. That object has to be a noun. I can obviously have more complex constructions than just subject, verb, object. But this is one way of writing a single rule from linguistics. And if you study linguistics, if you've seen or heard of link grammar, this is exactly what link grammar is. Link grammar is a collection of rules of this sort. It's called a lexis. There's a dictionary where I have a dictionary of words, and then I have attached to those words in that dictionary, in that lexis, what they can take as subjects or objects or adjectives or modifiers, adverbs of all sorts, prepositions, pronouns, you name it, how they connect up. The linked grammar system is a dictionary, is a collection of these jigsaw puzzle pieces that you can assemble. They're designed so you only get grammatically correct English language sentences when you connect them up. All right. I heard about chemistry all morning. This is intended for chemistry as well, right? There's something called the Krebs cycle or the citric acid cycle. It's the main process in your mitochondria which converts sugars into energy. And one of the ways that it does that is it converts adenosine diphosphate into adenosine triphosphate through a reaction called phosphorylation. And here's an example of a graphical diagram that does phosphorylation. It takes some molecule which has this phosphate attached to it, rips off that phosphate, attaches it to the adenosine, and leaves behind that molecule with a neuro-H on it. Well, it's just a graph element, right? So I'm going to represent the graph elements in the same way. I'm going to say, okay, here's a section, that's this thing. It's got two obvious inputs. Here's one, here's another. It's got two obvious outputs. I didn't list one of the outputs. Note I did something tricky here, right? In the previous slide, I had left and right. In this side, I'm going to have input and output. Previous slide, I said, okay, here's a type subject, type object. The thing itself was a word. Here I'm going to say, well, it's the name of a process. One of these inputs is a type because this thing R can be anything. I shouldn't say anything, but it's anything, any valid molecule that has a phosphate attached to it. This thing, the ADP, is not a type. It's a very specifically, it's that, right? And the output is going to be ATP. It's not going to be anything, but it's going to be ATP. So instead of saying I've got a type here, I've got a specific item. And the rules of connection are that I must attach specific items to specific items. Nil talked about theorem proving. Right, so here's an example of the same system for natural deduction. All right, so we're going to have some judgments. Right, I'm going to make a judgment that the proposition A is true, and I have another judgment that the proposition B is true. And using an ordinary rule of inference, I'm going to decide that the proposition A and B is also true. Classic logic gives this a name. It's called the rule of introduction. So this is a rule of introduction. It's got two inputs. It's got one output. The things that are coming in and are going out are propositions. Why? Why did we do this? Okay, so I'm going to wrap up this talk here, right? This is similar to what we've been doing with the atom space all along, with a slight change in terminology where I've explicitly made clear what can be connected to what. And the reason for that is all of that theoretical computer science behind it. From the natural language example, it's clear that what we're doing is parsing, right? If you have a dictionary, if you have a parser and you want to parse either natural language, or if you want to parse Java or C++, right? All compilers, or Python, all of these compilers and systems have a parser at the front end, which inputs Java or Python, or in this case, the English language, and some grammar specification for what's a valid grammar, so that I can take the syntax for it, right? That grammar expresses a syntax. That whole thing together is a language. A language is a collection of grammatically valid sentences. What did You know, right? What did these rules do? Well, they specified what a grammatically valid sentence looks like in chemistry or in logic, right? But these were all just graphs in the end, right? Here's a graph. It had two connectors and two connectors. So really, when I'm creating things, I'm creating graphs. In English, they're grammatically valid sentences, but the graph, you know, in biology, it's the valid ways in which molecules can interact with one another. Some molecules can connect to others. The immune system is famous for this, right? A connector on an immune system, right? The immunoglobulin, my tongue twister, right? Immunoglobulin, right? Has this funny little Y-shaped thingy with these variable sequences on the bottom of it, very highly variable sequences that can detect foreign, you know, that can detect, you know, it's an antigen, it can detect antigens and signal those to trigger the immune system for interacting. Well, those are based on a shape. There are two connectors and those connectors connect, right? This is a low-level synthetic biology version of the same thing, right? I'm just specifying a connector and a grammar of all of those things that can attach to it. Well, I talked about values before. So in fact, I can weight those connections with probabilities. I can call them Bayesian probabilities. I can, Ben's decade-old book on probabilistic logic networks. You can stick those values and those formulas on those connectors as well and crank through that machinery. The grammar has constraints, right? So this is a way of posing a constraint satisfaction problem, right? That this has to be connected to that. And then you apply a constraint solver to say, okay, these are the things that have to be connected. There's, you know, thousands, if not tens of thousands of computer science articles on how to solve constraint satisfaction problems. Here's how we can integrate all of that knowledge into the system. I had to throw in satisfiability modulo theories here, right? There's something called Boolean satisfiability. In Boolean satisfiability, you have a sequence of variables, which may be true or false, and then you want to find, and they're connected with and, or, and not. So if you say, if A and B or C and not D, find all of the truth value assignments which might satisfy that statement. That's called Boolean satisfiability. There's some very fast Boolean sat solvers out there. One of my favorites is in a constraint satisfaction system called answer set programming. It does marvelous things. Answer set programming looks just like Prolog, but is, I don't know, 1,000 times faster than Prolog ever was, 1,000,000 times faster than Prolog, because it took those logic and theorem proving algorithms and turned them on the side and let the satisfaction solver do the solutions instead of forward chaining and backward chaining. It replaced forward and backward chaining by satisfaction. So satisfiability modulo theories does the same thing, but then it tacks on, oh, it need not be and, or, and not. It need not be Boolean, but it can be anything in the middle. It can be equality. It can be relations. A relational database is a SAT solver with a theory of relationships. Right? The standard example, I think, is they say we have employee Joe Bob who works in the sales department and he makes $42 a year plus commissions. And you put that as a row in some table. Well, that row is a relationship, a triplet here, and Joe Bob and the sales department and his salary. That relationship, it's just a tuple, a collection of such tuples is basically, it's called a theory. And if I can, to do a database search, it's like, I want to find all the tuples that satisfy these relations. It's a satisfiability problem. So this is a generic, databases are generic examples of relational algebras working with a SAT solver. None of them use SAT solvers. Very few of them actually use SAT solvers under the covers, but that's because most databases were 30 years old, right? We can do that. Logical inference and deduction, well, okay, I guess I talked about that. Probabilistic. I already mentioned these things are tensors. So in fact, once you realize they're tensors, all of the concepts of tensor algebras apply. So I can use, hundreds of textbooks that have been spewed out on that and say, oh, well, yeah, sure, that's what we do here with the atom space. I can apply all that theory, deformation of, take the tensor algebra, mod it by another algebra. And that's what a deformation is, the quotient space. And well, I blasted right through this, so I think I've run to the conclusion here. I mean, okay, so the takeaway here is I'm trying to do something a little bit different than all the neural net, all the compact representations, all of the data dimensional reduction that has been talked about all morning. And I'm trying to go back and say, no, look, in real life, data is just naturally sparse. And that's just a fact, that you have to deal with. You can try to dimensionally reduce it. And obviously we've made a lot of progress with neural nets and with deep learning by compactifying that big sparse vector space into, a tiny vector space of, 300 or, well, I don't know, what are they up to, 1,000, maybe several thousand dimensional vectors and vector spaces. But in the end, it's really sparse data. This is what we have. Graphical representations for that data are natural. What's a graph? Well, a graph it's kind of an assembly of these jigsaw puzzle pieces where only those tabs that fit can be fit together. But that's what tensor index contraction is. Those, when you mate two tabs together, you're just saying, okay, it's a tensor and I contracted those two pieces. Well, but when I do that, I'm doing something called parsing, right? I'm back to computer science here. When I parse, that's all that I'm really doing. It's nothing fancier than that. It's nothing simpler than that. And I talked about values, right? What's the whole point of this? Well, I want to assign values to edges. I want to say, oh, well, there's some probability of this happening. Or I want to say, oh, there's some temperature or heat flow along this edge. Oh, or maybe that's the wind velocity direction. Values flow along those edges. And I'm not the first to notice this, right? Google called it TensorFlow for a reason. I call it a tensor with values that flow along the edges. Right? This is how you do a TensorFlow thing generically, not just with Python, not just with GPUs, but for any kind of data, for bio data, for language data, for logic data, you name it. So I'm trying to move the atom space, slowly but surely into this somewhat more general and more flexible generic setting. Haven't gotten very far, so I want to promote two of the projects that I'm trying to sort of keep moving. It's hard to do. One of them takes that representation and generates graphs with some probability. This is meant to, for instance, generate natural language sentences in English or some other language. Right? Link grammar is a Russian dictionary. We can generate sentences out of that. The hope is to apply this generic mechanism to generate sentences. Not just any sentences, but I said constraint satisfaction problem, right? Constrained sentences. Where did constraint satisfaction go? Oh, here it is. Right. Constraint satisfaction says, So when I say constraint satisfaction, together with language, I want to say, build me all of those grammatically valid sentences that involve the concept Ben, and involve the concept of eating, and involve the concept of pizza. And it'll say something like, Ben is eating pizza. Ben wants to eat pizza. Ben ate pizza. Ben will eat pizza. Someday, in the future, in the past. All right, well, that's just another graph that's satisfied some constraints. The constraints were the sentence must have those 3 words in it, but otherwise I use those generic jigsaw puzzle pieces to assemble valid sentences. Well, generating sentences is useless unless I know what the jigsaw puzzle pieces are, and so I've got a generic learning infrastructure for learning graph components given a large sampling of graphs. If I just suppose I give you 1 million graphs, what can I pull out of them? Can I pattern mine them to find out what's connected to what? And once I've pattern mined them to find out what's connected to what, I want to take those and promote those to being those jigsaw puzzle pieces, those graph components that can be assembled, and now reverse the process and do either parsing or do theorem proving or however within this infrastructure. And well, I think that's it for now. That's the conclusion of what I had to say. I'm hoping that all worked.
Yes, one moment. Let's see if Matthew can come online.
Just had to unmute there.
Yeah.
So there are a couple of questions from the community, and some of them are kind of related. So I'm trying to put them together somewhat. There's reference to, for example, Neo4j and how are we just building in another alternative to that? And you might have already addressed that after that question came in. But another question is, how does this compare to DSLs plus looking into the abstract syntax tree of the language for introspection?
Well, I can answer. It's straightforward. Well, part of this is the atom space is older than Neo4j, right? Neo4j just sort of took off and got very popular, but what we've been working on is a good bit older than that. It's also more general than Neo4j. Neo4j really, I mean, they focused on the immediate needs of application developers who needed to do certain things with graphs. They weren't really thinking about logic. They weren't thinking about probability. They weren't, any of this stuff that Nil was talking about, proving theorems of making inference chains, the book that you wrote, right? Probabilistic logic networks. That's not what the Neo4j guys were thinking about. They were doing something much simpler. As a result, I think their search mechanisms are much simpler, so I don't think they have the sophistication behind it. What they do have is they have a huge mind share, a huge, the world knows about them. The world does not really know about the atom space, and that might be a usability issue, a marketing issue, many reasons for that.
Yeah, I mean, there's a lot of particulars underlying what Linus is saying, right? So I mean, Neo4j for simple graphs and for traversals on graphs is cool, but I mean, if you have an acyclic hypergraph with links pointing to links, or a more general metagraph like with a link pointing to a subgraph, or if you have a variable node and you need queries that deal with the variables that are explicitly represented by variable nodes in the graph, or quantified variables in the graph, or you you need to do matching against knowledge base entries and queries in a concurrent way. I mean, none of this is in Neo4j. And in the end, if you need to take the stuff we do with the atom space and boil it into Neo4j, you're better off just to boil it into SQL than into Neo4j, given the limitations of how Neo4j works. So seems similar, but really the weighted labeled hypergraph with variables and quantifiers and links pointing to whole subgraphs. I mean, it's a different enough animal that the particular optimizations they've done in Neo4j actually are not really helpful for what we need to do, which is unfortunate, because it's very cool for what it is. And I think we need to emulate at a high level some of the things they've done in Neo4j in terms of scalability and usability, but we're also solving quite different problems.
Yeah, exactly. Actually, we try to make a very detailed comparison of Neo4j, the graph, and atom space, and it turned out that it's really difficult to map what can be expressed in atom space to Neo4j. And indeed, as Ben just have said, some things which are expressible in atom space and queryable in atom space, they cannot be done efficiently in Neo4j. So yeah, that's right. Yeah.
So another question, and I think this relates to some of the discussion we'll probably have tomorrow. Are you aiming to contain all knowledge and computational resources into atom space, or should it also become capable of, for example, interacting with third party or, for example, our own API?
That's like asking, do you need the knowledge in your brain, or should it be in the library, right? I mean, it's good the library's there, but you got to read it to get it into your mind to reason about it.
Well, the mutable values is one of the ways of moving knowledge in and out of the atom space. I mean, there's two ways of, right? The atom space represents knowledge. I like to think of that as being like plumbing, where, you know, you're a plumber, you attach a bunch of pipes, but then the knowledge that's flowing through it you can also think of it as being water, right? Or some fluid that is flowing through these pipes. And so the value subsystem is a way of saying, okay, here's an audio feed, here's a video feed, or maybe here's a feed of, I don't know, all the knowledge in Wikipedia or something. We're going to pipe it through this system. It's a way of attaching to the external world, and it's a way of attaching at a potentially a high bandwidth to deal with that. And yet I have this other low bandwidth system of the actual representation of the actual knowledge I learned from it. But if the meta question is, how do I make this usable so that ordinary programmers can deploy this in ordinary apps? That's a little bit harder. That's a conversation I'd love to have at some point with somebody. We'll seriously have that conversation, but it's not an easy one to have, because there are real trade-offs between what we want to do for AGI and what ordinary programmers want to do for ordinary applications. And bridging that divide is tricky. There was a question also about syntax trees, I think, and the answer to the syntax trees, abstract syntax trees, was kind of like, duh, yeah, that's exactly what this is. Abstract syntax trees, when you represent them that way, that's how you know you can manipulate them. So it not only it subsumes that. All compilers have that inside of them, and we've stolen this idea from compilers, right? That you need to have access to those trees in order to manipulate the data in them.
And another question that has come in, and it's very simple. It's, have you considered rewriting parts of the code base in Rust?
Me personally, Rust is becoming very popular. I mean, the Linux kernel is starting to, talk about admitting Rust code into the kernel base because it's thread safe and it has a lot of other nice properties that you want a programming language to have. So I'd say, sure, we can admit some of that code into the Atom space. Will I restart from scratch in Rust? Me personally, no. I'm busy. I got plenty to do. But I'll happily help someone else guide them along the way.
Yeah, this relates to some of what we're going to discuss tomorrow. I mean, Alexei and Vitaly and I and others are musing a rewrite from scratch of Atom space, among other options. And Rust has certainly popped up there as I mean, it's not going to be Python, right? It could be C++, but Rust is certainly a serious contender. And if we were to choose that, an awful lot of the lessons that Linus has learned so far are going to be incredibly critical to getting it right. Because I mean, the choice of programming language is an easy thing to talk about, but there's a lot of other subtler and more critical decisions that have to be made in such an undertaking.
Even before the language choice.
Well, the reason I mentioned the Linux kernel and Rust together is because the Linux kernel is right. I mean, several million lines of code written in C. I believe they admitted C++ not all that long ago because C++ is sufficiently compatible with C that it's not a complete rewrite. Right? And so the same conversation with Rust is that the idea is Rust is, you can trust it enough to not crash your operating system, because that's the one thing you must not do is crash your operating system, that it's reliable and dependable enough, and yet it'll interoperate with C just fine without performance quirks or blurbs or whatever. And so if you do want to pick another language to work in, you don't have to rewrite from scratch. You can just say, okay, we'll take those languages which are compatible with C++. And my understanding is that Rust is one of them, is that it's sufficiently stable and well thought out enough that you can use it for system if you can use it in the kernel, you can use it in an app.
Oh, it's very, very interesting language, right? I mean, it's imperative, but it has many of the formal verification properties that are typically associated with functional languages. So it's certainly serious candidate in my own mind. Huh? So another follow-up question: if all useful types of knowledge can and should be stored in a graph database, or if it's just used as a communication bus?
Yes.
A typical mathematician's answer
Yeah.
to your question.
Can you elaborate?
I don't know how to answer that. I mean, simple, right? Somebody's gotten the Atom space working on a Raspberry Pi, right? Not very much RAM. You can certainly jam data into it and pull data out of it. I think, what's one of the systems that's popular in automotive industry? I think it's called the Lynda tuple store or something like that, where you can jam in tuples and pull them back out using queries and rewriting, and it's
so yeah. I think the notion is with the weighted labeled hypergraph of Atom space, or and it's really generalized beyond the hypergraph, which is why I've started throwing the term metagraph around, which is even more general. Like a hypergraph can have nodes, can have links pointing to more than two nodes. A metagraph can also have links pointing to links, or links pointing to whole subgraphs. But I mean, with this sort of model, it is suitable for representing all sorts of knowledge, but of course there's both space and time scalability and processing issues. So I mean, I think mathematically you can map any kind of computable knowledge into that format. Using it as a communication bus, I mean, it's a cool idea. It's doable. There's obviously implementation issues and things being fast enough to get stuff in and out of a graph. But in OpenCog, yeah, the general notion is you're packing all the knowledge you need to really think about into this massive knowledge hypergraph or metagraph, and that's a representation that all the AI algorithms can work together on, right? So that when you're dealing with large scale, like sensory type data, there's many other issues to think about. Like if you have a huge library of videos, you don't necessarily need to take every pixel or voxel in all those videos and map them into the atom space. It's maybe too big. It's not as compact as just storing compressed videos. So what you're going to do there in practice is you're going to recognize certain patterns in the videos and map them into the atom space, and then they may link into the video repository itself, right? And then there's various levels at which you could do that. You ask, like, do we just use the atom space to store like what objects are where in the videos by some ontology of objects? Well, that's not really good enough for in-depth visual reasoning, right? So I mean, if you're working with a deep neural model of videos, then the question would be, do you create nodes and links in atom space corresponding to like just the upper levels of that hierarchical neural model of videos? Because and it's really a practical issue rather than a principle issue, because you could represent every voxel in all the videos in the hypergraph with no problem, but that may not be the most practical thing to do at the current moment, given that like video databases are huge and there's a certain amount of overhead in using the atom space. So then you're looking at atom space, which is a slightly to greatly abstraction representation with links into the video knowledge base.
Well, but that was the whole point of values, right? We made simple truth values generic into values, but those values can be streams of values, right? I said random stream is the tutorial.
You could do it, but like if
it could
like
be video or audio, right? I don't care.
If right now we had a contract to do analytics on all of YouTube's video database with OpenCog, we're not going to import the entire database of all YouTube's videos.
No, you misunderstand. The values never enter into the atom space. That's why I'm saying video and audio, right? They never are stored. Those pixels are never stored. When I have a audio stream value in the atom space, that doesn't mean I have the audio in the atom space. It just means I have a description of where the audio can be found and
right.
It needs to be sent to, where it came from, how it's going to be transformed, filtered, and where it's going to go to. That's what's in the atom space. It's like
what if you need to do some signal processing on the actual values in that stream? Then you have to do something else.
That's what the value does. It does, right? The atom space stores what kind of signal processing you want to do. The value says, I'm going to take audio from here. I'm going to apply a low pass filter. I'm going to apply a high pass filter. I'm going to mix it with a few sine waves. All of that is going to happen on a DSP or on a GPU.
So what happens when you want to use reasoning in OpenCog to learn a new filter?
I set up 5 or 10 or 20 different filters all running at the same time. And half of those filters, at the end of them, I'll put, say, a low pass filter. If that low pass filter finally flips over to all ones for more than a second, I say, I've found a pattern. I've data mined a new pattern. I'm not actually, all I'm looking at is that 1-bit signal that says, oh, the low pass filter finally triggered. I'm not looking at every bit that went through the
So the atom space is, in this case, the filters are defining the patterns in the low-level data that the atom space sees, and the data itself remains wherever it was, accessible as a stream by atom space.
the atom space describes the plumbing, the circuit board, right? The atom space describes, here's a wire that went from here and we plugged it into here, and here's another wire. It's like these old Moog synthesizers from a different era, right? They're just wires that you connected from here to there. The synthesizer did the work. All you have to do is move the wires around. So the wires are in the atom space. The wires tell you what's connected to what, but it's actually some DSP that's doing the hard work, or it's some GPU, or I don't know, 1,000 GPUs, right? Get some supercomputer to do the actual number crunching. The atom space describes where the numbers came from, what we're going to do with them, and where they go to. That's the abstract syntax tree. That's what that abstract syntax tree is doing. It's describing the flow of the data through the system. It doesn't have to do the flow itself. That's what the supercomputer does.
Yeah. So, I mean, getting back to the question as posed, I think what we're saying is raw data of various forms doesn't have to all be sucked into atom space explicitly. On the other hand, atom space can manipulate and look at patterns in this raw data as appropriate without sucking all into atom space. And your streams are one way of doing that. Alexei and Vitaly's cognitive module networks were a different way of doing that, but which had a similar property, that the raw visual data was being manipulated in TensorFlow, and their nodes were dealing with the TensorFlow computation graphs. It's different than the streams, but at a very high level, it's similar, because the nodes are representing they're pointing to patterns in this external, like high bandwidth floating point data, without having to suck every bit in these external images or audio files into nodes and links.
Well, I mean, this is where the streams came from, right? They originally came from, originally from the Hanson Robotics work as a way of handling the audio data. But then when Alexei started out, I sort of added a bunch of features and enhancements, and I was sort of surprised that they never got around to using them for whatever reason. But that's what the streams were kind of created for, was for them to be able to attach to the TensorFlow and to these cognitive modules. And then I guess maybe that's one reason I'm talking about them. Is like, here it is. The code is there. It's integrated with the atom space. It's been used. It's ready to be used again. Have at it. The API is, it's stable. It's proven. Hook it up to stuff. Hook it up to GPUs. Matt?
I think that's probably a good place to end. Lots of things.
Thanks, Linus. It's great to get a deep dive into some aspects of atom space, and there's so much there in the pattern matcher, which we hardly touched on. So I'd encourage anyone who wants to learn more about the plumbing here, look at atom space, but also the pattern matcher, which is in OpenCog GitHub, is really there's an awful lot there in terms of not just pattern matching, but sort of functional and logical program interpretation packed into the pattern matcher. And this relates to some stuff Alexei will talk about in his talk tomorrow, just about different ways of organizing everything that the pattern matcher does. So I mean, clearly, with all these talks today, we're barely scratching the surface of stuff that's in a huge code base and a huge amount of publications and so forth. But hopefully at least can give people who are watching this a sense that there's a lot of depth of thinking and a lot of experimentation and prototyping and useful practical work that's been done, a lot of code that's been written in, a direction of progress toward AGI, which, we haven't created AGI with it yet, but there's a lot of progress made in a direction wholly different than what you're reading about in the newspapers today, right? And if you come back tomorrow, where it's going to be a little different, not so much biology, but we're gonna be brainstorming more on possible future directions. Sort of how would we make a much better atom space, incorporating everything Linus has learned and has been doing. How will we reorganize pattern matching in different sorts of ways? How would we make all this stuff better leverage massively distributed computing resources? All questions that we certainly do not fully know the answer to yet by any means. And one of the reasons I've organized this event is wanting to pull more people's minds into helping think through all these things. Like these are very big problems and hard problems and difficult questions. And we're a small group of mad scientists trying to grapple with a huge amount of difficult puzzles. So we could certainly we can certainly use more help from anyone who's willing to throw their mind into it. So we'll join up again tomorrow morning, 8 a.m. Pacific time. Then thanks
Is it
everyone.
8 a.m. or 8:30?
I don't know. I thought it was 8. Let me
It's at
check.
8:30 on the page.
30.
Oh, cool! I get to sleep half an hour later. Then it's 8:30 a.m. tomorrow Pacific time. Even better. So, yeah, thanks everyone for your contributions today, and thanks to Ibi Benali and Matt Eclay for operating the event.